and then we will start in a few seconds. Okay, here we go.
Perfect.
Welcome back, everyone, to the Data Science Summer School 2025. We are very happy to have you here again. If you have just come back from our previous sessions on R and Python programming, but if you're new here, a very warm welcome to you as well. We're delighted that you can join us today. The summer school is organized by the Hertie School Data Science Lab, together with the generous support of the Hertie School and the Digital Foundations. It brings together a series of theoretical and hands-on workshops led by experts working at the intersection of data science and policy and social impact. And our goal for the summer school has always been to bring high-quality educations in data science to the public and to anyone around the world. And I'm very happy to see everyone from all corners of the world coming to join us for the summer school in the last couple of days. A little bit of housekeeping. So everyone in this session has your microphone and video turned off, as we have quite a large audience here. But you can put your question in the chat as well as in the Q&A, and the instructors will try to answer them when he can, or we will remind him when it's needed. And if you would like to speak, please feel free to raise your hands, but please do so close to the break or when the instructor asks if there's anyone have any questions. And we can unmute you and let you share your videos and your audio if you want to. And today's session is about applied calculus for data science. Understanding calculus is quite fundamental to data science and AI, and it underpins everything from optimizations, algorithms, to machine learning, to modeling change and uncertainties in dynamic systems. And so a solid grasp of these concepts really help us to move beyond the black box models that a lot of these AIs and deep learning models work on, and we can build more interpretable and more effective solutions in machine learning. And so to kick things off, I'm very pleased to introduce the instructor for today's sessions, Ilya Klebanov, who will be teaching the course today. Ilya is a mathematician. He's working in research group for numerical mathematics of deterministic and stochastic partial differential equations, led by Claudia Schillings at the Freie Universities of Berlin. And his research lies mainly at the fascinating crossroads of uncertainty quantifications, numerical analysis, and machine learning. And he focused on high-dimensional approximations of probability distributions, Bayesian inverse problems, density estimations, and kernel methods, topics that are super complex and also increasingly becoming central to data science today. And I hope he can also introduce and talk about some of these topics in today's sessions. And so please join me in welcoming Ilja, and let's dive into the mathematical foundations that will support your journey through data science this summer. Thank you. Up to you, Ilya.
Thank you very much for the kind introduction, Hui. So let me just share my slides, and then we can start. Okay. I hope they are visible. Okay. Okay, so thank you all for coming. I'm really happy to have such a big and great audience. Today's workshop will be on applied calculus for data science. And the outline is very simple. There will be an introduction, then we'll talk about calculus, then about data science, and then there will be a wrap-up. In the introduction, we'll cover just an overview on calculus, data science, and in particular learning theory and regression, and which will be followed by some motivations from real-world problems. Then we'll go over to calculus, where we will first discuss functions and their visualizations. And then we'll come to the main parts, which is differentiation and integration. So in differentiation, we will talk about derivatives and the chain rule. And then we'll go to higher dimensions and talk about partial derivatives and the gradient, and how this can be all applied to backpropagation in artificial neural networks. Okay, after that we'll talk about integration and how integration is related to differentiation, in particular about the fundamental theorem of calculus. Good, then we'll go over to the data science part, which I think is why you're mostly all here. but this will be only after the break because we will need all the bases from calculus to actually understand the data science part. We will talk about data and its distribution and how to learn functions. So basically, if you have the data, you first subdivide it into training set, validation set, and test set. Then we will talk about how to define correct loss functions and how to choose the hypothesis space, so the parametric space that you want to approximate your function by. And this will take quite a while, especially this choice of the hypothesis space. And after that, we'll talk about optimization, which is basically gradient descent and stochastic gradient descent. Okay, in the end, there will be a short wrap-up. We will have some key takeaways, and I will tell you what I did not cover in this workshop, and then I will suggest some further readings and resources. After that, we can have some questions if there are any left, but you can also ask questions in between. I will have short question breaks, and we'll also have some quiz questions in between to keep things slightly interactive, which I mean is hard given that it's an online workshop, but we'll do our best, right? Okay, let's begin with an introduction. So, what is calculus? Calculus is a subfield of mathematics which covers the topics of change and accumulation. Change, that's differential calculus, so derivatives. It talks about rates and slopes and sensitivities. So basically, how do small changes in the input affect changes in the output? And then there is integral calculus, which is about accumulation, which covers the topics of areas, totals, and distributions. And we will talk about this in a second. So why should we learn calculus? So calculus is basically everywhere in modern science because it's everywhere in data science and everywhere in machine learning. If you're doing medical diagnostics, you need to predict disease progressions. You have to model drug responses and detect sudden changes. So you really need to take care of the rates of change of certain signals. If you're doing financial forecasting, you have to optimize investment, you have to estimate the risk and minimize the risk and consider different price options. So you're taking gradients basically to find optimal solutions, right? You want to make good decisions, and for this you need to take gradients to minimize certain functionals or functions. Also, you use integrals to estimate certain expected values, for example, returns. In climate modeling, you're modeling the temperature change and the rainfall accumulation. And so again, you see that derivatives and integrals come in very naturally. And for self-driving cars, for example, you also need real-time decisions, path optimization, and you need to avoid obstacles, which all relies on minimization of time, of energy, or of certain risks. And finally, for machine learning models like ChatGPT and so on, you need to train models in very high dimensions, and for this you need loss minimization, and this is typically done by backpropagation, which is an application of the chain rule, which is also something that we will talk about as we talk about differentiation. Okay. What is data science? Data science is the practice of extracting knowledge from data. So you have certain data and you want to analyze it. What patterns do exist? What predictions can we make for future data points that come in? And it's all about, so there is this part of modeling prediction, which is all about doing forecasting, fitting functions, and basically analyzing data from that perspective. Then there is also inference, like hypothesis tests. Is some drug useful or not? How confident are we in our decisions? And this also involves uncertainty quantification, which is the field that I work in. And then there is also data preparation, which is sometimes forgotten. When you collect data, which is kind of the first step, you have to collect it, you have to clean it. Some data will be missing, you will have some outliers. So you have to clean the data. You have sometimes to transform the data or even reduce the dimension of the data. So there is some first pre-processing step, if you like, which is called data preparation, which is also crucial to data science. Okay, this is a short overview, a short Venn diagram of these different fields, because in some sense, machine learning, data science, and statistics, they're kind of all the same, but they are also kind of different. So they cover many similar topics, but from a different perspective, and they have kind of their own touches to it. So this is, oh, sorry, this is a short overview on how these interact. So deep learning is a subset basically of machine learning. There are certain algorithms used in machine learning, and machine learning can be seen as a subset of artificial intelligence. Data science is strongly overlapping with all three areas. And as I said, we already talked about what data science is all about. Statistics has a more mathematical and probabilistic flavor to it, so it's slightly more theoretical. And at the center of all of these three lies statistical learning theory, which might be slightly too small here. And we will talk about statistical learning theory in a second, mainly about regression. Okay, so learning theory or statistical learning theory consists of two or three subclasses. So there is supervised learning, where you have data that has been labeled, and you have unsupervised learning, where you have raw data that has no labels to it. There is also reinforcement learning, which is, for example, used for self-driving cars, etc. But we will not talk about this today at all. So let's focus on these two subsets. Supervised learning, as I said, someone actually sat down and labeled the data. And there are two subcategories. You basically want to learn functions in both cases, either classification or regression. Classification means that your output space is finite. So, for example, you have two classes in email spam detection. You want to say, okay, the red dots are all spam, the blue dots are all not spam. Here I visualize this in a two-dimensional plot. In reality, of course, it's much more high-dimensional because an email consists of many, many letters, obviously. So it's a very high-dimensional space, just represented here in this two-dimensional two-dimensional plot because I cannot visualize any higher dimensions. And the task of this email spam detection is to basically separate as good as possible the red points from the blue ones. Sometimes some red points might actually end up in that area, but if you would draw a line which is kind of separates them too precisely, this would be overfitting, which we will talk about a lot today, and it would generalize pretty badly to new data coming in. So if a new data comes in, a new email comes in, you want to classify it, and you need to say which set it belongs to, and for this you must not overfit, as we will see later on. Okay, but email spam detection is not the only thing. Of course, there is also medical diagnosis if a person is healthy or sick. For example, cancer, not cancer, diabetic, non-diabetic. There is image recognition where you want to say, okay, those are cats or dogs or I don't know, maybe planes, boats, whatever. It doesn't have to be two classes, right? We said that Y, the output space, has to be finite. It doesn't have to have just two classes. It can have 10 or 20 classes. For example, in image recognition, as I said, you have like a person, a boat, a car, I don't know, a cat, a dog, and so on, a tree. So the output can be an object from a wider set, a bigger set, but still finite. And then there is regression, where we are trying to learn functions in the continuous space. So the output space is now continuous. Think of the real line, if you like, and then you're not learning an output that is categorical, right? Just a finite set of possible objects, but you're learning a function, right? Which is used, for example, for weather prediction. If you want to predict tomorrow's weather doesn't have like a finite set of options, but tomorrow's weather is continuous. For example, the temperature is continuous. So you're trying to predict a continuous quantity. Similarly, in forecasting stock returns or predicting crop yield based on certain data from satellites or from the soil in agriculture. So basically any kind of prediction which is continuous falls into regression, prediction and forecasting. Okay, now let's come to the unsupervised learning part, where the data is raw, so we don't have labels, right? We don't have any example data where we have input and output as we had here. we basically have just the input, right? There is no output. Okay, so for example, the data can look like this, and then you can still analyze it, right? You can identify, oh, there seem to be three different clusters in that data, which maybe belong to certain subpopulations which we can separate, right? So identifying clusters is an important thing. For example, if you want to organize articles by topic, you have a lot of articles gathered, and depending on the words that appear in the articles, you can sort them by topic and find these clusters. Or identifying gene expressions in certain patterns in bioinformatics to predict how likely it is that a person might get a disease, for example. Then there is density estimation. So again, you're given some raw data, say in the two-dimensional space, and you're trying to estimate what probability distribution this data came from. And the probability distribution is often represented by a density. We are going to talk about this as well, and I suppose you're going to talk about this on Friday. So to identify the density that data came from is crucial in modeling the distribution and also to make predictions, right? For example, if you want to estimate the behavior of customers, the amount and timing of their next purchase, you need to estimate densities. Or if you're doing uncertainty quantification, you also need to estimate probability distributions and densities. And finally, the last topic that I have here, I mean, those are not the only topics, right? This is just a selection of them. And the last one that I want to show you is the dimensionality reduction and manifold learning. Sometimes, and actually almost always, high dimensional data isn't really spread across all dimensions evenly. Typically, the data lies on a much, much smaller submanifold, here represented by this Swiss roll dataset. And you see, actually, we are in the three-dimensional space. Each data point lives in 3 dimensions, but there is some underlying surface that the data lives in, which is 2-dimensional. You can ignore the color. The color is just for demonstration. And this thing kind of gets much more extreme in higher dimensions. So you can have images that are 10,000 dimensional, but actually you only need 20 dimensions to represent them properly, which is a good thing for compression, right? You have something that is 10,000 dimensional, so you need 10,000 numbers to represent it, but you can actually describe it by just 20 numbers, so you already can compress. So this is the idea behind the compression of data, image, video data, audio data, and so on. It's good for visualizing things, to get an intuition of things, to interpret things, and so on and so forth. Right. And what I wanted to say is that this step is often used before clustering and before classification. So first you identify the lower dimensional manifold, and if it's smaller dimension, then it's much more easy to cluster and classify, and all the algorithms that you use in these sub areas are much easier to perform once you have this reduction. Okay. I think the next topic is already calculus. So maybe are there any questions so far? Obviously, this was just an introduction, so we'll dive into these things in a second. But are there any questions so far? Okay.
Hi, Ilya.
Hi.
Alia is here, so I'm helping today your session.
Thanks.
We have 2 questions. One is classification and clustering seem very similar. Can you talk more about the difference? The first question. And the second question is from Shao Ria. What is label? Please share examples of labeled VC raw data.
Right. This is actually, those questions are actually connected. So I see I didn't do a good job in describing what labels are. So in classification, let's talk about classification as an example. Your data doesn't just come as, for example, images. So say you want to do image recognition, and you have images of dogs and of cats. In order for your algorithm to learn about which images are cats and dogs, if you get a new image, for example, you first need to learn on your training data, right? But to learn on your training data, you need the images that you have to have labels. You need someone to sit down and say, okay, we have 10,000 images. Which of them are cats? Which of them are dogs? So someone has to actually attribute these classes to the data that we are given. So once this is done, we have labeled data. As you see here, some points are red, some points are blue. For example, those can be cats, those can be dogs, or this can be spam and non-spam. And then you learn this hypersurface which separates the two. And then once a new image or a new email comes in, then it can be classified using using this hypersurface, using this rule, which tells you how to separate the two. But you need the labels first. You cannot just imagine you had the points without the markings. So all points would be black, right? Then you couldn't possibly find a separating hypersurface, right? Which separates one from the other. In clustering, however, the problem is different. You don't have labels. You only have the black dots. And the task is to identify subgroups, but these subgroups, you cannot really name them. You cannot say, oh, those are dogs, those are cats, because you don't know it. No one labeled them. Only after that, you can maybe analyze the clusters, have a look at them, at what's going on there. For example, in the articles, what topics are covered there. Maybe it's war or sports or weather or whatever. And then you can only afterwards say what these clusters actually mean. But the clusters a priori don't have any labels, so you don't need anyone to sit down and say, oh, this article does this and this article covers that topic. Okay, there is one more, I think. Let's give you an example how manifold surface is used in real cases. Okay, let's go to manifold learning. Okay, so for example, if you want to do classification, classification works better the lower the dimension is, typically. If you have a very high dimensional problem and you apply a certain classification algorithm, it will often not work too well. But if you first identify the dimension, the kind of the underlying manifold, then you first project the data onto the manifold, then you are in, say, 20 dimensions. And in 20 dimensions, you can much more efficiently do classification. So if you're doing classification, you're typically first doing dimensionality reduction. This is one application. But also, as I said, if you're doing image compression or video compression or audio compression, you try to learn the manifold, project your data point onto the manifold. So you have basically an encoder, which tells you how to save your high dimensional image or video into a lower dimensional object. And then you have also a decoder, which tells you how, so this one you store, right? And you can store millions of them, millions of images very efficiently. And then you have a decoder, which is basically a program which tells you how to extract back the high dimensional point from that low dimensional object. And this high dimensional point is then again your video, so you can show it to a person, right? Show it to the image or the video to a friend, for example, right? And use it. Okay, there are many questions. This is good. An example. The quality of the labeling process is critical.
The quality of the labeling process is critical. If something is mislabeled, the decisions made by the algorithm will be wrong. Or if a label stereotypical is assigned to an object, or it can lead to bias. Will you speak about these ethical aspects later? And the last question is zero-shot classification example of classification or also unsupervised learning? Ilya, maybe it's easier for you to answer all these questions at the end of the session, or
right, maybe this is easier. Let me just answer that. I will not go into the ethical aspects of data science. I will try to answer the other questions at the end of the workshop. Otherwise, it might get too too much and we will get too slow.
Exactly. Thank you.
But it's totally right that wrongly specified data can cause problems, especially ethical problems, which is discussed a lot. So there is a lot of ethical machine learning questions present. This will not be part of this workshop, unfortunately, but it's a very interesting topic. Okay, so let's move on to calculus. As I said, calculus is the mathematical field which deals with change and accumulation, so differentiation and integration. But we first need to talk about functions. And before we talk about functions, we need to talk about numbers. And I will not talk about numbers too much because we have to start somewhere. So I'll basically assume that you have some familiarity with real numbers. It doesn't have to be much. You basically have to know that the real numbers is basically a real line where the numbers are kind of represented, right? So there is natural numbers, 1, 2, 3, and so on. Sometimes 0 is also considered a natural number. Then if you go to the integers, you also include all the negative numbers, negative natural numbers. Then the rational numbers are all possible fractions of such numbers, and except where that b must not be 0, of course, you cannot divide by 0. And then the real numbers are the completion. Mathematically, it's the completion of these rational numbers. The point is that if you look at the rational numbers and you basically think of them as lying on a line, there are many holes in the real numbers. And these holes, actually there are more holes than non-holes, surprisingly. Those holes, like, for example, the square root of 2 is missing, pi is missing, the Euler number is missing. These holes are filled by the real numbers. This is the basic idea. So you can basically approximate the square root of 2 arbitrarily well by a sequence of rational numbers, but you cannot represent the square root of 2 as such a quotient, such a fraction, right? And this is actually not so hard to prove. It's an interesting proof, but we are not going to do it today because of time limitations. So these cannot be represented as fractions, but these still lie kind of on the line and can be approximated arbitrarily well by rational numbers. And this is called the completion. And then we really have a continuous, nice space, which we call the real numbers. Then there's also complex numbers, which we'll also not go into today. Okay, now let's talk about functions. Functions are triplets consisting of a domain where the inputs live, the codomain where the outputs live, and the function itself, which is the assignment. So, and the functions describe relations between inputs and outputs. And for this relation, every x has to be assigned exactly one value y. There are other relations in mathematics as well, but functional relations have this property that every x needs to be assigned exactly one value. Different x can be assigned the same value. This is allowed, or certain values might not be assigned at all. Certain values y, but every x must get its y. So for example, f can live, as I said, it can live on an arbitrary set x and map to an arbitrary set y. And the numbers 1, 2, and 5, for example, now have to be mapped. And 1 has to be mapped to a unique element from this set. For example, to the element c. It cannot be mapped to c and b. It has to be unique for each of these 3 numbers, but not all of those have to be hit, kind of, right? And some are allowed to be hit several times. So for example, such a thing, which assigns 1 the letter C, 2 the letter A, 5 the letter A, this is a function. And I'm sure you have seen certain functions in school or in your university life. For example, the parabola x mapping to x squared is a function from the real lines to the real line. But you can also, of course, since only non-negative values are actually hit by that function, right? You can also consider it as a mapping from R to the non-negative part of the real line, right? The interval from 0 to infinity, excluding infinity. For me, this is a different function. it has the same graph, right? But it is a different function because the codomain is different, right? Remember, the function is a triplet, and if one part of the triplet is different, then it's a different function. Also, we can change the domain, of course, but if we change the domain, and for example, we change it to only the non-negative part, then we are left, we actually change the graph, right? We are left with only the right part of the graph because we only can input x's which are non-negative. Okay, the next example for a function is the plus function. So our operation plus is actually also a function. I wrote it in quotation marks because our notation is slightly different for plus. We typically write x1 plus x2 and not plus of x1, x2 as we would for a function. The domain here is actually more complicated because the domain has now two inputs, right? We have to take a sum. We need to have two inputs. So we have r times r. This is a notation for taking the product of the two, and the product of sets means you take all possible pairs. Okay, so this set is the set of pairs x1, x2, where x1 is a real number and x2 is a real number. And the output is then one real number, namely the sum of the two. So the input can be 3 and 5, and the output would be 8, right? And of course, we can generalize this to the product of more than just one real line, Rn, which has all tuples of length n. And we can sum the tuples, and the notation for this is this sigma notation. So the sigma I from 1 to n over xi is nothing else than the sum over all the xi. Okay? And of course, you can leave out the brackets if you like and just write this because summation does not care about the order. Good. I think also in school we typically learn about linear functions and affine functions. Affine functions have an offset b, which is basically the shift in the y direction, and a slope a, right? If you plug in the value 0 for x, you will get a times 0 plus b. A times 0 is 0, so you get b. So this is why the offset is b. And a, as I said, gives you the slope. And a and b are certain parameters from the real numbers, certain values, certain fixed values. And this you can also generalize to higher dimensions. For example, if you consider affine functions from Rn to Rm, functions from Rn to Rm is nothing else than m different functions written one beneath the other. And these m functions, in the affine case, written one beneath the other, looks like this. So you have certain fixed values a11, a12 to a1n. You multiply them by x1, x2, and so on. You add them all up, and then you add some offset. And this is you do this for every component, right? For every of these m functions, and then you get a vector in Rm. And this is why we have these double index notation, because we have the index for a matching the x's, and we have the other index saying which function, which of the m functions this belongs to. And there is a shorthand notation for it, which you are going to learn tomorrow, I guess, in linear algebra, by writing this as a matrix vector product plus some vector, which is then also called the offset or bias. And the matrix is then such a table, basically, of numbers, and B is a vector, B1 to Bm. So you have to imagine this basically as a plane, if you like, in higher dimensions. It's not slightly misleading, but it's a good intuition for the time being. And this is something that you're going to learn, as I said, tomorrow in more detail. Okay. And then there are, of course, all kinds of functions. For example, the sigmoid, you can combine all possible functions that you can think about. You can plug in x, take its negative, take its exponential, add 1, and then take the inverse. And this gives you the so-called sigmoid function, which has this nice S-formed shape going from 0 and almost reaching the value 1. So almost reaching the value 0 here and almost reaching the value 1 here, and having this nice symmetric form. Or you can take several inputs for example, two inputs and do cosine of x1 and multiply it by the exponential of x2, which gives you this nice function here. And this brings us to our next topic, which is visualization. So what do we actually see here? How do we visualize a function which maps from r times r, which is r2, to r? Okay, so let's talk about visualization. So I think functions from r1 to r1, I think you basically know how to visualize them. You plug in the value, each value on the x-axis, say the value 2, you plug it into the function, you get a result, in this case, maybe the value 5 or something, and you draw that point with the coordinates 2, 5. And if you do this for every point and connect them, then you get this line, right? You basically don't even have to connect them, because if you draw the points, then they are already on the line. As long as it's continuous, you already have the function plot. So you plot a dot for every pair and you get a line. If you do this, if you consider functions from R2 to R1, things are slightly more complicated. Now you have the input has 2 dimensions and the output has 1 dimension. So you need basically 3 dimensions to visualize it, roughly speaking. So this brings us to this nice surface plot. And the way that it works is the following. If you your input now has 2 coordinates, right? Say 1 and 2. So this point here with coordinates 1 and 2 is your input x. You can plug it into the function, you get a new number, which is just a real number because the function maps to R1, and then you draw the point in R3, with the coordinates 1, 2, f of that point. So you basically go up from here and draw the corresponding point. And if you do this for all pairs, this will build you this surface, this hillside landscape, if you like, of a function, right? So this is how things are visualized in 2D. But there is also a different visualization possible, the contour plot. The contour plot is actually cheating because you're visualizing something which is 3-dimensional in 2D. And I think all of you know this from topographic maps, right? If you look at a map of, say, some mountain ridge or the Alps, for example, then you will see these topographic maps which tell you where are the peaks, where are the valleys, and so on. And they are represented by these level lines, these level curves. These level curves, or contour lines, what do they mean? They mean that along this contour line, for example, all the values, the function has all the same values. They all have the value roughly 1.75 or something, right? On this level line. So all these x's, right? Each point here is a pair, x1, x2. All these x's are mapped to the same value, 1.75, and all x's on, say, this line are all mapped to 1.55, and all x's on this orange line here are mapped to 1.95, and so on. So this is, I think you can see the connection between the two, right? Here you have these 4 wells, if you like, and you have this hill in the middle, and you have the mountain going up left and right as x1 grows larger. Okay, some people use contour plots, some use the filled contour plots, which is the same thing, just with filled with color. So roughly speaking, the 3rd dimension is represented by color instead of plotting 3 dimensions. And the advantage is that you can much more easily identify minima, for example. So if you want to say, oh, what exactly is the x, what are the x coordinates of this well, it's actually pretty hard to say in this plot, right? You would have to somehow project it down or try to turn the surface around, while in the contour plot you can say, oh, okay, the minimum is somewhere here at -1 and roughly 1.5. Okay, so for me, contour plots are somehow nicer. I usually work with contour plots because they are easier to grasp and also faster to plot. Okay. Oh, now comes the first quiz. So I'll give you 1 minute to draw, maybe on a piece of paper. Don't use any program, please, to draw the function which maps x1 and x2 to their product, x1 times x2. How do you think would the surface plot look like, and also the contour plot look like? Okay, I'll make a short break and give you 1 minute to try it out by yourself. Just try to draw and try to think of which values are assigned which values, and draw this function. Okay, so 1 minute is over. So let's talk about this function. Does it look like? So the first thing that we can notice is that if we plug in 0 for x1, we get 0. So the whole y-axis or the whole x2 axis will have the value 0, will be assigned the value 0. Also, if x2 is equal to 0, the product is 0, so the whole x1 axis will be assigned the value 0. So we have this cross of zeros, which is easy, I guess, to understand. And now we'll talk about diagonals. So let me just draw the function and we'll talk about it. So if you look, so again, you see the cross, it's 0 and 0. Also, you can see here, if you look very precisely along this line, all the values are 0, and also along this line, all values are 0. The function values are 0 in this direction. So those are really assigned the value 0. Now let's look at this diagonal first. So if you take this diagonal, those are pairs 1, 1, 2, 2, 3, 3, and so on. They are mapped to 1 times 1, so 1 squared, 2 squared, 3 squared, and so on. So this will be a parabola, a slightly stretched parabola in that direction, which you see here, right? You get a parabola in this direction. And on the other diagonal, you get the values 1 minus 1, 2 minus 2, 3 minus 3. So you'll get minus that parabola in this direction. So a parabola which is opened in this direction, right? And if you combine the two, or actually the four, you have the cross and you have the two parabolas, you get this nice saddle surface, which is called a hyperbolic surface because all the level sets are hyperbolas, which is represents this function. Okay. There are some questions. Okay, is there any function that has one input and multiple outputs? Well, that depends on what you mean by one input, multiple outputs. So if you can have a function that has only one element in its domain and 3 elements in its codomain, but only one of these 3 elements will actually be hit, right? You cannot map this one element in the domain to several elements in the codomain. This is not allowed. This would not be a function. It would be a different kind of relation, but not a function. Okay. There was also a hand raising. Alia, can you help me with this? Maybe later.
Yes,
Yes.
yes.
You can.
So what do you need?
I think
Sorry.
someone raised a hand. I'm not sure.
All right. No, actually, no one raised. There only a question.
Okay, so that was the question. Okay, very good. No, someone else raised. Oh, there for the quiz. What does the void space mean? I don't understand which void space. Sorry, I don't get that question.
See how, Chen, could you please, things outside the contour. So that he meant by the void space.
Do you mean this? Are you referring to this line here?
It seems so.
So this line is there to represent which space between the contour. So wait a second, between the contour lines. Do you mean the void here in the middle? Are you saying what? So basically, we would like to draw all possible contour lines, but it's not possible because there are infinitely many lines. So this is kind of what happens if we start drawing certain lines for certain function values, right? We draw contour lines for certain values. You can actually define the values, the f values that should be plotted, and then you plot all points x which map to that value, and this gives you the contour line. And certain x's don't just hit certain any of these fixed f values, and then there is this white space. But you can also fill it up. You can also color the whole thing by a filled contour plot if you like. I hope this answers the question.
Yes, there was also a.
There's not a question, but it doesn't seem to be a question, more like an explanation. Yeah. So if you have a saddle-shaped surface, a surface plot, it's not any, but this specific hyperbolic surface, then the contour lines which will actually be hyperbolas, which are functions which have a certain mathematical description. Okay.
Yeah. Okay, we're getting more questions.
Yes. Again, I think we will try to shift the questions to later on. I see I'll have to make room for more questions at the end.
Thank you.
Okay.
Thank you, Ilya.
So let's move on and talk about further visualizations of functions. We talked about functions from R2 to R1. Let's now talk about functions from R1 to R2, which are typically thought of as trajectories. So, and also often they are just considered on some sub-interval of R1, not on the all of R1. And the trajectory looks like this. You basically start drawing your point. So for each, you think of it as time, right? The input as time, and for each time point, you just simply plot the output, and the output is a point in R2, so you get a point basically moving in space, right? In this in space, by space meaning in this plane in this case, if you are in R2. Again, you are losing some information because actually you have one input, two outputs. You would need a three-dimensional space to represent it. And you could do it. You could basically put in a third dimension representing the time. But this would be harder to grasp. This trajectory is easier to grasp, but you lose some information. Basically, this is just kind of your trace in the snow. So if you see if someone went through the snow and you see their path through the snow, you will know where they went, but you won't know exactly at what time they were at which point. So they could have gone through the first half very quickly and very slowly through the second half, or the other way around. If you simply plot the trajectory, you won't know this. This can be fixed again by color or other means of visualization, but in this primitive plot, you will only see the trajectory itself and not the whole function. Anyway, I think this for many applications, this is enough information, and this is very often the way that it's plotted. Okay, now we will talk about functions from R2 to R2. So we would need a four-dimensional space to represent them. So this is very hard to plot theoretically. So there are two ways basically that I'm aware of, two basic ways to plot such functions. One, if you're talking about transformations, so basically functions which are mappings one-to-one from some original space to some final space, then you can just draw a grid and look where each grid point is mapped to. So basically you have a grid here, you take a point here, check the output. Oh, okay, the output is here, and this is where I draw a point. So you have many, many points, then you connect them by the lines, and you get this transformed grid. And in order to know which point is mapped, which point from the original grid is mapped to which point in the transformed grid, you typically use some color. It's actually sufficient to use just 2 points, color just 2 points, because if you color these 2 points, you know where this point is mapped and you know where this point is mapped. And just by following lines, you can then know for any other point where it's mapped to. So you know the exact correspondence between the points here and the points here. So this is one way to visualize transformations from R2 to R2. If your function from R2 to R2 has a different interpretation, namely a vector field, a velocity field, you can also plot it with this so-called quiver plot, which works the following way. Let me maybe try to draw this. So say you have a point. Oh, does it work? Oh no, I'm doing here. Okay. So you have a point here. Let me use different color. You have a point here, and you're that you can compute where it's mapped to, and say it's mapped to this point here. Okay. Then you draw a connecting line or an arrow from the origin to that point, and then you basically take that arrow and shift it over here and draw the arrow here. Okay, the arrow is not perfectly aligned, but I hope you get my meaning. And it's much easier to understand if you think about it really as a velocity field of some fluid. Every point is assigned a velocity where so the direction and is represented by the direction of the arrow, and the velocity strength is represented by the length of the arrow, and that arrow you just draw at that point, right? So then this will tell you how the fluid or the gas or whatever you have is moving around in space. I hope that makes sense. So this is a very good way to represent vector fields and velocity fields. But it doesn't have to be these physical things, right? So velocity fields, we think of it with fluids or gases, but that doesn't have to be the case. So for example, the x input and the y input don't have to be actual coordinates, and that doesn't have to be a gas. It can be also some populations. For example, you can have rabbit population on the x-axis and fox population on the y-axis. And then the arrows tell you how the population would evolve in this so-called predator-prey model. So let us go through this. Can I actually delete the arrows again? Apparently not. Okay, but it doesn't really matter. Let's start again. So say you start in this point here. Okay, let's use new color so we know that this is a new interpretation. Okay, so you start in this point here. So you have quite many rabbits and quite few foxes. Then, since there are few foxes, the rabbits can reproduce easily and are not eaten too much by the foxes. So the rabbit population will grow. The fox population has a lot to eat because there are many rabbits, so it will also grow, but not too fast because there are just too few foxes to reproduce. So you will get these two. So both populations will grow, and you get these two arrows, which are combined to this one arrow here. So your population will go in this direction, right? Both populations will grow. And they will grow up to a certain point where there are many foxes, right? Many, many rabbits, many, many foxes, but so many foxes that the rabbits are being eaten too much. Not too much, actually. Actually, there is still a balance, so this is kind of the balance point. There are so many foxes that the reproduction rate of the rabbits corresponds to how much of them are being eaten. So the population of the rabbits no longer increases. So we don't have any, it doesn't increase or doesn't decrease. So we don't have any change in that direction. But the foxes, they have enough to eat because there are really many rabbits now, right? They have reproduced like hell, and so they can reproduce further, so we'll get more foxes as time goes on. And this will go on and go on and go on. But the rabbit population then will start to decrease because there are many rabbits, so they reproduce, but there are more and more foxes who eat them. And so the population will decrease up to this point where there are really, really many foxes. And yeah, still many rabbits. And the fox population is increasing and increasing and increasing because there are still many rabbits to eat. But at some point, the number of rabbits, it's decreasing, right? The number of rabbits is decreasing. So we are now at this point where there are many foxes and not too many rabbits. Still a lot, but not too many. And not enough for this large fox population to eat. So the fox population will then also start decreasing, right? So both populations are now decreasing. We get fewer rabbits because there are many foxes who eat them, and we get fewer foxes because there are many, many foxes and only few rabbits to eat. So both populations will decrease up to this point. And I think I don't have to explain the further details. It's clear that at some point there will be a few rabbits and few foxes, so the rabbits can reproduce again, and we'll get back to the cycle, and we will get this typical predator-prey behavior, or not typical, but very simplified predator-prey behavior that has been first described by Lotka and Volterra, I think, in the beginning of the 20th century. So this is called the Lotka-Volterra model, if you want to Google this. So yeah, so I hope it's clear how these arrows represent the dynamics and how the arrows represent a function from R2 to R2, which describes this dynamics. The dynamics describes an ordinary differential equation. I'm slightly sad that we won't have time today to talk about ordinary differential equations. First, because it's a very important field. ODEs describe all kinds of motions, motions of planets, motions of fluids, and so on. Phenomena like epidemics, how many are diseased, how many are healed, and so on. So ODEs can describe a lot of different things, and I would like to talk about it more, but we simply don't have the time. Also, ODEs have a lot of applications in machine learning and data science, so it's worth learning about it, but it's out of scope for today. Okay. Good. So I think visualizing functions is very important to learn about machine learning and data science and everything else in mathematics as well, because this really gives you some intuition that guides you in your understanding. This is why I took so much time to explain it. I think the next slide. Oh God. Okay. I don't know why, but somehow this stays over the slides, so I will just close and reopen the document. Sorry for this. Come on. Okay, I hope you can all see this, and let's move down to I think here. Yes. Okay, no more drawings for today. Okay, let me just check the chat for a second. I used to choose. You can clean drawings. Yeah, this is a good hint. I suppose I can. The question is, how will this panel used to choose colors? Okay. Thanks for your hint, Alexander. Okay, and questions and answers. Let me just check. Okay. Okay, I think some of these questions will be answered as we go to the second part of the talk. So I will try to answer them, all of them later. Okay. Oh, actually, one question I think I should answer now. Why is it called R2 to R2 if there is only one domain, the rebel population? No, it's not one domain. It's, if you look closely, the x-axis is the rebel population, the y-axis is the fox population. So x1, the first input, is the current rebel population. The x2 is the current fox population. And the output we draw as an arrow from the input point itself. So starting from the input point, we draw the arrow. This is how we represent such a function. Okay. Now let's talk about composition of functions. If we have two functions, f mapping from x to y and g mapping from y to z, we can compose them. So first apply f. We have some input x, we apply f of x. Then f of x is an element of y. And since g is defined on y, we can apply g to f of x, right? We can apply g to f of x, and we will get a new element in z. So we get a composed function which has input x and spits out an element in z, which is g of f of x, and we denote it by g circ f. Okay, so for example, we can first square our number x and then plug it into cosine, to the cosine function. Then h is the composition of the parabola f of x equals x squared and the cosine function. And the quiz, again, there is a short quiz. How does h look like? What do you think how h will look like? And I would like you to draw it for yourself and try to imagine how h looks like. And I give you, again, 1 minute to maybe half a minute maybe to try to draw the function h. For those who don't know it, this is how the cosine looks like. I plotted it here again, so you have some idea of how it works. I will try this commenting part stuff in the beginning. Ha! Okay. Okay, I think that was maybe enough time. So let's talk about how this will look like. So for the cosine function, if you plug in pi, we get the value -1. If we plug in 2pi, we get the value 1. So for the function cosine of x squared, if we plug in the square root of pi, we will get the number -1. And if we plug in the value square root of 2pi, we will get the value 1. So the interval here, so this whole line here will be squeezed to the interval square root of pi, square root of 2pi. And in general, what I maybe should have said first, the output of h of x is some output of the cosine. So in the end, you get cosine of something, and cosine of something always lives between -1 and 1. So if your picture that you drew somehow leaves the interval, the y interval -1, 1, then you're wrong. It has to stay in that interval. Okay, and this is how it looks like. As I said, the square root of pi is mapped to -1. The square root of 2pi is mapped to 1. And since square root of 2pi and the square roots are closer than pi and 2pi, this line gets squeezed in between them. And the lines get squeezed more and more as we move out because the x squared function becomes steeper and steeper. So it kind of the points that map to the corresponding values get closer and closer to one another, right? This is the case as x grows, but for small x, the situation is reversed. For small x, x squared is really, really flat, not steep, right? So the x squared function. So there, for example, if we plug in the value, say 0.5, you would have to see 0.5 squared is 0.25, so smaller. So the interval 0.25 here, from 0 to 0.25, actually gets stretched to the interval 0 to 0.5. I hope this is you get my meaning. So depending on how x squared behaves, how steep it is, we get either a squeezing and squashing or a stretching, right? And this is how the function then looks like. Good. Okay, Jay raised a hand. Okay, I guess I can. Aliyah, could you let Jay talk?
Yes, I asked him to unmute.
Yes.
And Jay, can you talk? Oh, well, he's not responding, I'm afraid. So, yeah.
I'm afraid we have to move on. Okay, in the interest of time, we move on. So let's talk about composition of more than one function. So if you have several functions, f1 to fn, with consecutive spaces. So this is important. f1 has to map x1 to x2, and f2 has to go from x2 to x3. It cannot map from some different space. Otherwise, we cannot compose them. Then we can compose all of these functions and we write them as fn circ, fn minus 1 circ, and so on circ, f2 circ, f1. So we first apply f1 to x, which is an element from x1. Oh, sorry, there is an index 1 missing. I actually put it there. 1. Then this will be an element from x2. Since it's an element from x2, we may apply f2 to it, and then we may apply f3 to the output, and so on. And in the end, we apply fn. Let me delete this again so it won't disturb us. And the example that I want to show you for this are feed-forward neural networks. So feed-forward neural networks, it's a very, I wouldn't say it's complicated per se, but it's kind of lengthy. It's a big function, a big composition of many functions, consisting of several so-called layers, which is nothing else than this function composition. And in each layer, actually two functions are applied. First, an affine function, which we have seen before. So this is our matrix A from before, and this is our shift or bias or offset B from before. So you apply a matrix times X plus B, but they have these indices L because there are several different layers, so we'll have several of those. And this function we call FWLBL, and those are affine functions, right, as we have seen before. W8L are called the weight matrices, and BL are called the biases. And they are actually then learned from data. So those are the parameters of the function that will be learned, and the x's are the inputs. And then after applying the affine function, you apply an activation function sigma, which is typically a simple function like the sigmoid or they are called ReLU and tangents hyperbolicus and so on. Think of the sigmoid function if you like, and it's applied component-wise, right? So the output of this guy will be a vector, not an element in R. So we actually cannot apply sigma to it, but we can apply sigma component-wise. So there will be a slight abuse of notation. When I write, we apply sigma to the output, it means we apply it component-wise. So to each component separately to get a new vector. And this is what we get. If we then combine all the layers, we'll first apply our first affine function, then apply the activation function, then apply the next affine function, then apply the next activation function, and so on. If we didn't put in the activation functions, we would just get one linear function. So the activation functions kind of make things interesting. Otherwise, things would just be linear. And we also could have just written one function instead of several layers of linear functions. So the sigmas kind of make things interesting. And if we stack many layers, this is nothing else than applying these functions one after the other that is composing them. X is called the input layer. Then the layers that you kind of don't see are the hidden layers, and the result, the output, is then given by the output layer. This is just machine learning terminology, and let me show you how this is typically visualized. To me, I really don't need this visualization because I know it's just a composition of functions, affine, sigmoid, or other activation functions. But sometimes such an illustration can help. So you have some input layer where your input lives. You apply, as I said, your first affine transformation and then sigma to it, get a new vector represented by these numbers here. It doesn't have to be 4-dimensional, it can be 5-dimensional, it can be 1000-dimensional. That depends on basically how you build your architecture, how big you set up your matrix to be. And then you apply the next transformation and sigma function, the next transformation, activation function, and so on. And at some point, you get the output layer. I hope this makes things clear. So this is a feed-forward neural network, a very simple one. And as you know, or maybe you have heard, those are used a lot now because this is the basis of deep learning. This is kind of the core of all of deep learning, setting up such an architecture and then learning the parameters W and B. Okay. Good, we are done with functions and examples and visualizations. Now we come to differentiation. So the first kind of big topic is differentiation. Differentiation tries to compute the slope of a function. How does it work? So if you have some nice function f, you look and you want to consider the slope at the point x star, so basically the slope of the tangent line. What you can do, instead of looking at the tangent line, which is hard to define directly, you look at a point x star plus delta x and look at the function value there. And you consider, instead of the tangent line, you consider the second line, this line here, which connects the 2 points. And you look at the slope of that second line. And for the second line, we construct this slope triangle, which tells us how to compute the slope. The slope triangle gives us the slope by dividing delta y by delta x. And delta y, recall how we constructed these 2 points, delta y is simply the difference between f evaluated at the shifted point and f of the point we are interested in, right? So you compute this, the slope of this triangle, which will not be exactly the derivative, right? This will be, if the triangle is big, it will be far from the derivative, from the slope at this point. But if we take now the limit to 0, so we take delta x and try to make it smaller and smaller, then we start approaching the tangent line. And if we take the actual limit, we'll get the tangent line or the slope of the tangent line itself. So this is what happens in differentiation. This is how it's defined. We take the derivative to be the limit of this ratio delta y by delta x. And I'm sorry, I cannot go too much into limits, right? Again, for time reasons, typically if I would teach an analysis or a calculus course, I would first introduce series. I would first then introduce limits of or sequences in series, and then introduce limits of sequences in series. And then we'll talk about limits of functions, and that would take weeks. So for now, we can only work with less mathematical rigor and just this intuition of the triangle getting smaller and smaller to finally eventually give us this derivative. For the notation, it's sometimes denoted df by dx or d by dxf. This is all the same notation for f prime for f prime. And the intuition that one should have is sensitivity. So basically, if I have some error in the input x star, so if I wiggle around a little bit here, how will my y values, my output values, wiggle around? And the derivative answers this question, but only for small wiggles. So for small errors in the input, it tells us by which factor they will be scaled to give our delta y, right? This comes directly from this slope triangle. We get directly this relation, except that it's an approximation because this only holds for actually delta x going to 0. So in practice, only for small delta x. Okay. And there is some physical intuition to it, of course. Maybe this also oftentimes helps to get some physical intuition. So if your x-axis is time and your y-axis is the position s or displacement, then if your position changed gradually over time, right, with the same velocity, then you would get this velocity by dividing the difference that you go in space by the difference in time. So if you go, I don't know, 20 kilometers and you do this in 20 minutes, then you're doing 60 kilometers per hour, right? So you would take the delta y and you would divide, or delta s in this case, and would divide by the delta t. If your velocity varies, right? You're driving a car, sometimes you are faster, sometimes you are slower, and you want to know the current velocity at a certain point in time, then you would actually need to make this triangle smaller, right? You would try to look at how much distance you would maybe cover within 5 seconds and then scale it up, right? And this would give you a more momentary derivative, a more momentary velocity, which then will be the derivative. So the derivative of the position with respect to time is exactly the velocity at that time point. S prime of t is v of t. Okay, so that was the derivative at one specific point. Now we can take the derivatives at every point, right? So for example, we can take it at this point. Here the slope is positive because the function is growing. Here the slope is negative, so the derivative is negative. Here it's just slightly positive. Here it's really strongly positive, a large positive value. And we can then plot all these values that we get over x, or over x star, if you like. So you get a new function for every x. We get a value of the derivative. And this is what we plot. So if the derivative is positive, like in this point, we plot a positive value. If it's negative, we plot a negative value with the corresponding value, basically, right, for the slope, and so on. And then we get this nice new curve, which is the derivative of f. There are a few points which are called critical points, maxima and minima. So here, for example, we have we have here a maximum, right? A local maximum. Here we go up and then we go down. So here is a local maximum of the function. Here the derivative has the value 0, right? Because the slope is 0. The function at that point is flat. We're not going up or down. So the derivative is 0. So also at the local minimum, the derivative is 0. And so-called saddle points, there also the derivative is 0. That's where the function is flat, and you can identify them very easily. The other points are sometimes harder to identify, but it's always clear where the function is, where the derivative is positive and where it's negative. It's positive where the original function grows and negative where it decays. Okay, and then there are certain rules how to differentiate, which are then typically proven then in calculus. We don't have really time for this, so I'll just give you the rules and you have to take them as they are. The derivative of a monomial, x to the power of n, is simply n times the monomial of a degree lower, x to the power of n minus 1. The derivative of the exponential function is the exponential function. The derivative of the logarithm is 1 over x. The derivative of sine is cosine. The derivative of cosine is minus sine. And the derivative of the tangent of x is 1 plus the tangent squared. Okay, so for this course, those are just given. Okay. In your quiz, I would like you to try to draw the derivative or to sketch the derivative of this function. I will give you again 1 minute for this. What would you think roughly would the derivative of this function look like? Okay. Okay, so let's have a look at this function. So the best way to plot the derivative is to first plot the zeros of the derivative, which are exactly the points where the function is flat. So the function is flat on this line, the function is flat here, so where you have a local maximum or minimum, right? So you directly get all the zeros of your derivative, and then you just have to think on which intervals between these how does the function behave? So here the function is decreasing, so our derivative will be negative, so it will go like this. On this interval, the original function is increasing, so our derivative will go like this. Okay, so altogether we get such a curve. The derivative is positive, we go up until we reach the maximum where it's 0, then it goes down, so we have a negative value for the derivative until we get to the minimum where the derivative is 0 again, then it starts growing again, so the derivative is positive, and so on, right? Here it's very steep, so it's very positive. I see I drew the thick line slightly too wide. Actually, it's only 0 starting from here to here, but I hope you get my meaning. So this is how you can think of the derivative. I think this is a good exercise. Okay. Now we come to the chain rule. The chain rule tells you how to compute the derivative of composed functions. So you have a composition of functions, f and g, and you want to compute the derivative of the composition g circ f. For this, we introduce y star, which is f of x star, and z star, which is g of y star, which of course is then g circ f of x star, because y is f of x star. And then we know that let's talk about errors, right? The output error of g delta z is roughly speaking g prime of y star times the input error for g. But the input error for g itself is the output error of f, right? Y is f of x. So we can replace delta y by f prime of x star delta x, right? This is exactly what we had here, right? Our old intuition for the sensitivity interpretation of differentiation. And for y star, I simply plugged in f of x star. And so you see that the small changes, delta x, in the input result in certain changes in the output. Namely, you take the input and you multiply it by this value. So this is just an approximation, but for small delta x, the approximation gets more and more exact. So for delta x going to 0, we get equalities here, and this factor, this new factor, this becomes the derivative. So the chain rule says the derivative of the composition of g and f is g prime evaluated at the right point, y star, remember? So you have to evaluate it at the right point. This is sometimes done wrong by when applied the first time. You really have to apply it in the right point, f of x star. That's the only meaningful point to apply it to. And then really multiply it by the inner, so-called inner derivative. So this is the outer derivative, this is the inner derivative, because g is outside, f is inside. F prime at the point x star. A mnemonic way to put it or to remember it is to consider delta z by delta x and plug in the delta y in the numerator and the denominator and rewrite it as delta z by delta y by delta x. It's good for remembering things, but I don't like it too much because it doesn't tell you at which point to evaluate the derivatives. So yeah, so let's do a very short quiz. I don't think we need much time for this, maybe 10 seconds. Try to do the derivative of cosine of x squared. Okay, so what we have to do, we have to take the outer derivative first. The derivative of cosine is minus sine. We forget completely what's here on the inside. We can ignore it for the time being and just write minus sine. Then we recall what is on the inside. It's x squared. So we write down x squared. It's minus sine of x squared, of f of x star, right? And then we multiply it by the inner derivative. The derivative of x squared is 2 times x by our differentiation rules for monomials. So we get the derivative of f is minus sine of x squared times 2x. Okay, so this is how you can compute it. A few things that I also just mentioned. There are rules for products and for quotients of functions as well, how to derive them. But they're called the product rule and the quotient rule, but we will not go into these, and they won't be relevant for this workshop at least, but of course they are very relevant for calculus because in all kinds of places you have to take derivatives of products and quotients. Okay, our next topic is differentiation in higher dimensions. So since we are going to talk about neural networks and data science and machine learning, we need to cover higher dimensions at some point. And this is where we begin. So we will start with partial derivatives. Partial derivatives look at the change of f in a certain direction. For example, in the direction of x1 or in the direction of x2. So it fixes all the other inputs and only changes the jth input. So if you want to take the partial derivative with respect to coordinate j, say x1, then you fix all the other coordinates, x1 star and xn star, and only change the j coordinate. You add a certain shift in that direction. And then you make, again, the slope of the second, right? The slope triangle for this. So you subtract the original f value and you divide by delta xj. How does it look like? So basically what you're doing by fixing all the other values, you're looking you're looking at the cross section. At the cross section where you only change the x1 value, but no longer change the x2 value. This will give you the derivative. If you look at this cross section and consider the cross section curve, this blue curve here, which is basically the function restricted to this very specific set, to this line, then this is a one-dimensional function, right? It's just a line. And for this, we know how to compute the derivative, right? We just take the slope of the tangent. So you look at this cross-section curve, you look at the tangent at that specific point, and you take the derivative. And similarly, you do this for the second direction and take the derivative in x2 direction, right? So you basically make things one-dimensional by fixing all other arguments. Okay. So those are partial derivatives. And they're very important because they describe the model sensitivity to certain inputs. Those inputs can be the features, the inputs themselves, the axis basically, or certain parameters. If you take the derivative with respect to some parameters, this is also allowed. You can take the derivative with respect to parameters. And then it gives you the sensitivity with respect to these parameters or inputs. And then you can interpret this by saying, okay, the output varies a lot with respect to that parameter, but doesn't really change when we vary this other parameter. So maybe this other parameter doesn't play such a big role, or this input doesn't play such a big role, right? For example, in medical data, if you want to make a diagnosis, and you can check which measurements actually played a role in making the diagnosis, right? If your function maps inputs, which are measurements, to a diagnosis, then you can say which measurements are more important for the diagnosis by checking the sensitivity, right? So this is why partial derivatives are very important. And another reason why partial derivatives are very important is that from partial derivatives, we build the gradient. And I think maybe if you have heard the term gradient or gradient descent, which is a very important term, which we will come to later when we talk about data science. So let's define the gradient. The gradient at a point x star is simply the vector of partial derivatives. And I want to give you a very good intuition for the gradient. This is important to me. So let's try to get a good grip of it. So imagine our function here. I think you now have good intuition on how these contour plots work. So there is a hill, and this way you go up the hill. And if you look at the partial derivative in this direction, then think of it really as being on that hill. Imagine yourself standing on that hill and looking in that direction. Then the derivative will be pretty high, right? Because in that direction, the hill is rather steep, while in the x2 direction, the hill is not so steep. You almost go along the contour lines where the f value is just constant. So you basically don't gain any height in that direction. So this is maybe what children would call a shortcut, right? When they first climb a mountain, they would say, "Oh, can we just go this direction instead of taking the winding serpentine way? We just go up the mountain straightly." And then very quickly they realize, no, this is probably not the best idea. So to be very precise, the arrow that I drew is the partial derivatives times the first unit vector. So the partial derivative is just a number. In order to plot an arrow, I multiply it by the first unit vector, which is a vector of unit length in that direction. And similarly here, I multiply it by a vector of unit length in that direction so that I get these two arrows, which together build up this blue arrow, the gradient. And I think from this picture, it becomes clear that the gradient then really shows up the hill in exactly the steepest possible direction, because you basically take kind of the weighted mean of these two, right? Not exactly, but I think it's a good interpretation to say this one enters stronger than this one, so you go more in x1 direction than in x2 direction, because in that direction you actually don't go up so steeply. So this will give you the steepest possible direction. So the gradient points in the direction of steepest ascent, which is the fastest increase of the function. And its length is actually the rate of increase, so the slope in that specific direction, which I will not go too much into. One thing that I want to stress, which is not super important, but I think it might help at some situations. The gradient, if you really imagine this hill, the gradient does not point up the hill. Okay, it's not a three-dimensional vector. It's a two-dimensional vector. It's the vector in the x1, x2 plane pointing right in this flat plane, but it points in the direction where your steepest increase is. Okay, so it's a kind of if you would point your arrow at the steepest direction, and then you take the x1, x2 projection of it, right? So that's the direction it points to. It's a vector that lives in Rd, not in Rd plus 1, or Rn, not in Rn plus 1. Okay, that's maybe just more of a detail, but I think it's important to know. Okay. Then there is also the total derivative. If you have a function going from Rn to Rm, you can build a total derivative, which is called the Jacobian, which is then a matrix of derivatives. So you take function, so again, a function f from Rn to Rm is nothing different than m different functions, okay, from Rn to R1. So you can take these functions and take the partial derivatives with respect to all the inputs and just simply put them all in this table, which is a matrix. And this guy is called the total derivative, or Jacobian, the Jacobian of a function. For each x star, you get a matrix. And note that if your function actually goes to R1, then you basically get this row vector here, and the gradient nabla f of x star was the corresponding column vector. So this guy is nothing else than the gradient transposed. So basically, if you look here, you take the gradient of all the f's, but you write it down row-wise, right? The gradient itself is a column vector. Okay. And with this Jacobian, we can formulate the chain rule in higher dimensions, which is very simple. Recall the chain rule in one dimension. You take the outer derivative at f of x star times the inner derivative. The same works now for the Jacobian. The Jacobian of the composition is the outer derivative evaluated in f of x star times the inner derivative. The only thing that is important now, this is a matrix times matrix product, which you're going to learn about tomorrow. And the order matters. Well, here, in principle, I could have put the f prime before the g prime. Here, this has to be on the left, this has to be on the right. So keep it this way, never change it. Okay. With this chain rule, we can finally do backpropagation. Backpropagation is nothing else than applying the chain rule again and again and again and again to a feed-forward neural network. The only thing that's important, we take the derivative not with respect to the input, and this is slightly confusing, but with respect to the parameters. Because, as we will see later in the data science part, we want to optimize the parameters, so we need to do gradient descent with respect to the parameters, so we need to compute the gradient with respect to the parameters, or the derivative with respect to the parameters. For the affine functions, it's very easy. So taking the derivative of an affine function with respect to x, let's first do the input, you just get the matrix. That's the same as if you differentiate ax plus b, right? You get a. If you take the derivative with respect to the matrix, you get x transposed. And if you take the derivative with respect to the offset, you get the identity matrix, which I will not write down here. Okay, so this is how you take the derivatives, and you need all of them in order to propagate back the chain rule through these compositions of functions. Okay. The activation functions, they are applied component-wise, so this is really just a one-dimensional derivative, and you can choose the activation function, right? So you choose them just so simple that you can basically write down the derivative explicitly analytically, if you like. Like for the sigmoid function, for example, you can write down explicitly the derivative, and it's very cheap to compute. Again, important, backpropagation computes gradients with respect to the parameters, not with respect to the inputs. You need the derivatives with respect to the inputs in between to get the chain rule right, to really propagate the chain rule backwards, because it's this composition of functions. But in the end, you're only interested in the derivative with respect to the parameters. Okay. This finalizes differentiation. Very good, we are right in time. I will check the questions. Okay, if I have some data such as a curve, how can I describe it using a function? This is something that we will come to soon in the data science part. Mohammed Said Islam wrote, will it be a function? Does it qualify vertical test from the contour graph? So no, it's the other way around. First, you take a function, and if it's a function, then you can draw the contour plot. Otherwise, you cannot draw the contour plot because you don't know which values are taken for each x. If you have several values attributed to it or assigned to it. Okay, Boldanova Daria writes, I'd appreciate if you could explain how applied calculus for data science is applied in public policy. Let me write this down. Maybe I will explain this later when we come to the data science part. So f prime of x plot shows the changes which is depicted in the graph. Yes, exactly. So f prime of x shows exactly the slope, the value of the slope at each point x. Okay, I hope this roughly answers the questions, but there is one more coming in. Oh no, Aliyah is writing. Okay, thanks, Aliyah. Okay, then we can move on. Our next topic is integration. And this is our last topic before the break, so stay with me. Integration generalizes the notion of area under the curve, at least if you're one-dimensional. So given a function g, you want to compute the area between the function and the x-axis. And the integral from a to b, so these are the integration limits, a and b, g of x dx, gives you then this blue area here for a equals 0 and b equals 3 in this case. It can be assigned area. So if the function becomes negative, then some of the area might be negative, and then you have to subtract that part from the positive part. And the integral itself can be negative. So you have to take care of the sign slightly. How is the integral defined? Someone raised their hands. Maybe Aliyah, maybe you can unmute Benjamin.
Yes, he's unmuted. He's not
perfect.
muted.
Benjamin, can you ask your questions? Okay. Maybe that was a mistake, or it was raising of a hand by accident. So I guess we'll move on. If you have a question, you can raise your hand again later. Okay, so we move on with the integral. How is the integral defined? Well, the basic idea is computing the area is difficult, right? Directly. So what we do is we split the area into rectangles of certain heights and compute the area of the rectangles. The area of the rectangles is easy to compute. It's the base length times the height. And so we can compute these and add them all up. The base length, if we break it up in capital N even line segments, then the length of each segment will be b minus 1 over n. And we multiply it by the function value, g of xn, and add them all up. Okay? And then, again, as for the derivative, we take the limit. The limit for this mesh getting finer and finer. Right? And as the mesh gets finer, I think you see that we get closer and closer to the area that we are interested in. Again, maybe some physical intuition. This is exactly what you would do if you wanted to compute the distance that you traveled over some interval of time. You would split up your interval into several segments and say, okay, for the first 5 minutes, we went with this velocity, so we covered that distance. For the next few minutes, we went with that velocity, so we covered that distance. And then you would add up all these separate distances, right? The distance for constant velocity is just velocity times the time interval. So that's what you would get. And the finer you choose your discretization, the better your approximation will be. And in the end, if you want to compute the actual distance travel, you need to take the limit with the delta t going to 0. And this gives us another rule, which is kind of interesting, that the distance traveled between time t0 and time t1 is the integral over the derivative from t0 to t1. So in some sense, taking the derivative and taking the integral are inverse operations. I hope you see this. So you take the derivative and then the integral, you get back to the actual quantity, right? Let's put it in a more general setting. So derivatives describe rates of change. Say you consider how your wealth changes, and then you take the derivative, which is your income. Then if you then integrate over your income, you get back your wealth, right? Or the difference, at least, of your wealth, or if you integrate over that time, right? So the integration and differentiation are kind of inverse operation, because the integral measures how the quantity accumulates, which is exactly the inverse operation to taking slopes or rates of change. So this gives us the fundamental theorem of calculus. If you take the derivative of some function f and integrate from a to b, it's the difference of the f values of b and of a, right? As an example, if you integrate the function 1 over x, we know 1 over x is the derivative of log, of the logarithm, the natural logarithm. So we have to take log of b minus log of a. And another way to put it is if we consider the function capital G of x by integrating from a to x. Okay, so x is now the upper integration limit, a is some fixed number, and x now changes, and we integrate up to that limit the function g of t dt, then this function g will satisfy that its derivative is g of x. How can we see it? Well, pretty easy. Say you already know a function f, the derivative of which is g. Then what will g of x be? G of x is the integral over g of t dt. So by the fundamental theorem of calculus, we would get f of the upper limit minus f of the lower limit of the integral. So this is exactly what we would get from this formula. And hence, if we take the derivative of this function, we have to take the derivative of f, which is f prime, and we have to take the derivative of f of a, which is just a constant because a is constant. So the derivative will be 0, right? The constant doesn't change, so the derivative is 0. And f prime of x is g of x by assumption. So g prime of x is g of x. There is another intuition for it. Maybe I will, if I have time, I will go into it a little more. Actually, why not now? There's no time like now. We can also try to do this now. So let's try to draw this. So assume you have a function g and you want to integrate it. And say here is a, here is x, and here is x plus delta x. And you have your function g. Sorry. Okay. Then let's look at the quantity g of x plus delta x minus g of x. This is the quantity, and divided by delta x. That's the quantity that we need to consider to find the derivative of capital G, right? As we take the limit of delta x to 0. But what is this value? How can we interpret this value g of x plus delta x minus g of x? This difference, well, g of x plus delta x is the whole area up to here, the whole area. Oh, let me take this pen here. So again, g of x plus delta x is the whole area up to here. G of x is the area up to x. That's how g is defined, right? G of x is the area up to x. G of x plus delta x is the area up to here. So the difference is the area of this space here. So let me draw this. What is this? Does it work? Okay, not how I expected it to work, but it's fine. So this area, this is g of x plus delta x minus g of x. Oh, it vanishes. That's what it was. Let me check it again. So let's use a marker. I think marker is what I wanted. Okay. Right, so this quantity is this area. Okay, good. And now imagine the delta x going to 0. What would happen to this area? We would roughly, since g, at least in this my assumption, I mean it's continuous, sufficiently nice, then the rectangle will become smaller. It's not a rectangle, right? It's a complicated area, but it gets closer and closer to a rectangle, right? Because the values of g are kind of getting closer and closer to the values of x. And very roughly, this becomes, so obviously, first of all, let's write down what it is exactly. So 1 second. So this is exactly the integral from x to x plus delta x, g of t dt. And this is approximately, for small delta x, if we can assume that g is constant on that interval, it's approximately g of x times delta x. Do you see this? Because as delta x gets smaller, we get something that is more and more looks like a rectangle, and we can really approximate it by a rectangle by saying, okay, since the values of g get closer and closer to g of x, we can basically say that the function is constant on that interval because we get so close to it. So this is the intuition behind it. So we get basically g of x times delta x. So the whole guy, if we divide it by delta x, then becomes roughly g of x. And that's what it is. The gradient, the derivative of g is, of capital G is little g in the limit. I hope that was understandable. Okay, let me delete all of this. And we go further. Not comment, okay. Now another quiz. Let's try, sorry, I forgot to say, this g is called the antiderivative of little g, right? So any function, the derivative of which is little g, is called antiderivative, which is kind of intuitive. It's the opposite operation, the inverse operation, so we call it antiderivative. And let's try to sketch the antiderivative of this function little g. You can use a to be this left value, this value right on the left, and start integrating from here if you like, but it's really up to you. So I give you 1 more minute to find this integral. So to find the antiderivative. Okay, so let's try to sketch it. Maybe let me try to sketch it here without showing you the actual plot, so we can think while we draw. It's always better to think while drawing. Let's try to sketch the derivative of that function. So we start in 0. The integral from here to here is 0 because nothing has been added yet. And I really want you to think of the little function g as your income. Okay, and the function capital G, which we are going to plot, will be your wealth. Okay, so you accumulate wealth by getting more income, and the income is your earnings minus your spendings. So sometimes your earnings are higher than your spendings, and sometimes your spendings are higher, so your income is actually negative, right? Like in this area. So let's start drawing. In the beginning, your income is positive, so your wealth is growing up to that point here, right? At that point, your income is zero because you start spending exactly as much as you earn, and in fact, it gets even worse. You spend more than you earn, so your wealth goes down. It might even become negative at some point. You are getting better. Your income is still negative, but you are getting slightly better here. And at some point, your earnings become positive, and in fact, they become really positive. Look at you go. You're doing great, earning a lot of money, and your wealth is growing rapidly. Up to this point, I mean, after that also, your income is still really large. So it keeps growing up to roughly this point here, when your wealth starts becoming constant. Actually, this is a pretty healthy state of mind, I think. So you spend as much as you earn. So this is a healthy situation. You don't accumulate any wealth. You have already some wealth from beforehand, but you don't gain anything else. But then somehow you lose your job or something, and at some point your value becomes negative again. Sorry, so your income becomes negative again, so your wealth is decreasing up to this point when it starts increasing again, and now you really, and now you really have an even healthier situation, maybe, where you in each month you have some money left over. You earn slightly more than you spend, so your income is positive, and at this point you get a constant income, which lets your wealth grow linearly. So this is how the function should look like roughly. Let's see if I did a good job by checking the actual function. Okay, not too bad. Wait, did I somehow switch the colors in my plots? Oh, I apologize. Somehow the colors get switched in the plot. That's something I should fix. So the blue one somehow becomes orange, but I hope you get my meaning. Okay, let's erase everything again. Now I know how to do it, thanks to Sasha. And we go on with integration in higher dimensions. So I hope you all understood with this little exercise how integration in one dimension works and how to compute antiderivatives, or at least sketch them. Now let's talk about integration in higher dimensions, which corresponds to volumes or hypervolumes in even higher dimensions under the surface. So let's do the two-dimensional example first. So the two-dimensional example is a three-dimensional picture, right? Because the function goes from R2 to R1. And say you want to compute the volume beneath the curve on that rectangle. So here we have the contour plot where we really see nicely the rectangle, the area over which we want to compute. This corresponds to our interval a to b from the previous topic. But now we really have some region. It doesn't have to be a rectangle. It can be a circle. It can be an ellipse. It can look weird. It has to be measurable. So I will not go into details here. Cannot be some weird fractal kind of thing, but it doesn't have to be a rectangle. That's what I'm saying. And then the integral is defined as being the volume between the graph and the domain A, right? In the x1, x2 plane. So this volume here. How can we compute it? Actually, how can we define it properly and also compute it? That's by using a mesh. For example, you can split your region A into smaller rectangles, such a mesh, and consider these cuboids and take the volume of these cuboids by taking the area, the base area, or actually it's a base volume then in higher dimensions, base d-dimensional volume times the function value at that point, or at any point within that rectangle. And this gives you the volume of the cuboid, and then you add all the cuboids together. And as you make the mesh finer and finer and finer, then you get a better and better approximation of this volume here, right? So this is integration in higher dimensions, and I will talk about an important application for it, which is a teaser for Friday. Friday will be the workshop on probability and statistics. So I will introduce now what a probability density function is. And for this, we really need to understand what an integral is, and we will do it in 1 dimension and in 2 dimensions to get a really good understanding and intuition for integrals. So a probability density function of some random quantity, whatever that is, x, describes the probability of that random quantity taking certain values, and it does so in the following way. It's the probability that x happens to lie between a and b is the integral of that density. This is how a density works. Let's make an example. Oh, sorry. Okay, so there are a few obvious properties. First of all, it's non-negative. Otherwise, we might get negative probabilities, which is weird. And also, the integral from minus infinity to plus infinity, so of the whole real line over the density, should be 1. Because for x to lie somewhere, that probability is 100%. Which in 100% mathematically described is simply the value 1. Let's make an example. So say you go out on the street and you pick a random person without looking at them, and you ask them for their height. I mean, it's a weird thing to do, but say you do this. So this would be a random experiment, and the output would be a random quantity x, the body height of that random person that you took. And then what you will find maybe is that certain heights are more common than other heights. And you would like to plot such a curve telling you which heights are more probable than others. So we would already intuitively maybe plot this line in some sense, which kind of tells you how probable which height is. But we have to be clear how to interpret this line, because each height separately has probability 0, right? Having height exactly 1 meter 70 centimeters 0.23456, the probability for this value is 0. Only if we look at intervals of values, then we can assign actual probabilities to it. And this is how probability densities work. The probability of that person that you randomly take from the population lying within 150 centimeters and 185 centimeters will turn out to be roughly 81%, the integral over that interval of your density. If such a density exists, this is how a density, if it exists, describes the probability, and this is what you are going to learn on Friday in more detail. Now let's turn to RD. We will do a 2-dimensional example. Same thing. You have a random quantity z, which takes values in RD now. For example, a vector. This could be body height and body weight, the pair. What's the probability for that pair to land in a certain region A, subset of R2 or RD in general? Well, again, if a probability density exists, then this is the relation that it has to satisfy. And we will make the example of x being the age of the random person that you pick, and y being the height of the random person that you pick. And these quantities are not independent, of course, because as your age increases, at least as a child, your height also increases. And if you get really old, your height also decreases. And this is why you get a probability density which looks something like this. I want you to just to think a little bit about it, what that means. What does it mean? So for that random person to have roughly age 60 and roughly be 170 or 160 tall, that's pretty high. But for the person to be 60 and be 100 centimeters tall, that's almost 0, right? The probability for a 10-year-old to be 180 is also 0, but the probability for a 10-year-old to be somewhere between, say, 100 and 140 is almost 100%. So all of the 10 euros are somewhere here in between. I should mention the data that I used to do these plots. It's from the NHANES data, which is actually a pretty good data set, but it doesn't represent the whole population evenly. In particular, there are some babies missing, as you can see. Doesn't cover babies, so everyone in the data set started with 80 centimeters, which is of course unrealistic, but I think for the sake of presentation, it totally works for us. So what you see is, as a small giant, you tend to grow pretty fast until you're like 15, 16, or 18 years old, and then you basically keep that height. There is some variance to that because there are many different people, but as your age increases, you somehow shrink slightly in the end. So this is how the probability density would look like, and here is how it would look like as a hill, as a surface plot. Okay, and now, if you want to know what's the probability for that random person that you pick to be between 30 and 60 years old, and at the same time be between 120 and 180 tall, that means that your random quantity z, which is the pair x and y, lands in that rectangle. That is the integral, the volume here, the integral over that rectangle of the probability density, which is that volume here. Okay. I hope this is intuitive enough. If there are any questions, I will take them later. And let's make a short quiz. Actually, we made that quiz online. Maybe Hui or Elia, maybe you can help me with that. At least you promised to help me to
Yes,
take the. Yes.
I shared in the chat for everyone.
Thanks. So yeah, so in the chat there is a link to this homepage where we'll take a quiz, namely the quiz on calculus. Did you share the quiz on calculus?
Yes, it's the quiz for calculus.
Great. So okay, I would all like you to join the quiz, and then you can reply to the answers, I guess, once I think you have like 15 seconds to answer the question once I allow it. Okay, so how do I do it? Present. Reveal the winner. Yeah, we don't have a winner. Okay, let's try to present it. Okay, can you all see the quiz? We really have to help me with this. So we are still waiting for the players to enter. I think you can now enter the quiz. Okay, I'll just guess I hope that you are all in there. And we will start the quiz now. There will be no points. I just want you to do the quiz just for fun, basically. So, what is the gradient of a scalar valued function from Rd to R at a certain point x star? Is it a matrix, a vector, a scalar, or a function? And the answer is a vector, but that doesn't seem to have worked. Can you clarify, since you can't enter?
Yes,
Okay.
I'm trying
You
to
didn't
see.
start the quiz. I didn't start the quiz. I did start the quiz. Wait.
It might just be that Menti is having some issues.
Okay. So if Menti doesn't work, it's not a big issue because we can always do it in the slides, which is not a problem. I just won't see your answers, which is also fine. So let's do the quiz here. So what is the gradient of a scalar valued function from Rd to R at a point x star in Rd? A matrix, a vector, a scalar, or a function? And the answer is a vector, because it's the vector of the partial derivatives. What does it mean if the gradient of a function is 0 at a point? The function is constant, the function is increasing, it's a critical point, a possible mean, max, or saddle point, a min, max, or saddle point, or the function is non-differentiable. And the correct answer is it's a critical point, because if the derivative is 0, there is no slope, it's flat. So it's either a min, a max, or a saddle. If it was 0 everywhere, then it would be a constant. But since we only set it at a point, then that point is a critical point. Okay, next question. If the derivative of a function is 0 everywhere, what can we conclude? The function has no minimum, the function is constant, the function is non-differentiable, or the function has a maximum at 0. And the answer is, I think I just actually just said it for the previous question, is that the function is constant. If it's 0 everywhere, it has to be flat everywhere, so it's a constant function. Okay, now I think we will have a break of 15 minutes, and I'll see you for the data science part in 15 minutes. Have a good break. Okay, 15 minutes have passed. I hope you're all back. Welcome back. We will continue with data science in a second, but there was actually a good question which I would like to answer shortly. What's the difference between P of h comma height and P of h given P of height given h, so the conditional probability compared to the join probability? And let me explain it very shortly. Actually, it's a question for probability and statistics for Friday, and but I think like the questions, so I think it's interesting. So let me just answer it shortly. So the joint probability, I think you have seen, right? The conditional probability, say P of, I think it was, did he ask for height given h? I guess. So for y given x, and I typically write x equals little x. I mean, there are different notations. Is so say your age, you condition on the age of 30, then the conditional probability of y given x equals x is described by the following density. You take the cross section for the age 30, which is, opa, come on, which is this cross section here. It goes like this, and then it goes up, somehow like this, right? This cross section area. And since you condition on x being equal to x, you're not interested in any other x's. You look at the probability density, how it grows and falls, here how it grows and falls along that line, and you look at this probability density here, at this function, this cross-section curve gives you the new probability density, almost. This probability density will not be normalized. It will not integrate to 1. So the integral will not be 100%. So you need to rescale it. You need to, basically to multiply it by a factor such that the integral is 1. And this is the conditional density of height, given that the age is 30 years old. Okay, and more on this, I hope, on Friday. Let me discard these pictures, and let's move on to data science. Oh, come on. Anything else? Yeah, you're welcome. Okay. Okay, data science, and we will focus mostly on statistical learning theory. And from that part, from the statistical learning theory part, we will focus mostly, actually only, on regression. But regression is really a big part of it, okay? So don't think of it as being 1/5, but think of it as being to me at least, the most interesting part, the most prominent part, the one that I use for predictions and decision making. The others are also very important, but many ideas from regression are also transferred to the others. So let's talk about regression. Sorry. Okay. So again, what's the goal of regression? The goal of regression is to learn a function which goes from some set x to some set y, and the set y now is a subset of Rd, so of a continuous space. And in our case, this will only be R1, the real line, for simplicity. And we want to learn this function from data. And we will adopt a statistical approach, meaning the data that comes in, those are realizations of random quantities, random variables. And they follow a certain density, pxy. That's why I introduced the densities before. So our assumption is that the data, that the output, y, is some f star, some true underlying function, the so-called data generating model, data generating function, applied to x, plus some noise, right? So there is some functional relationship, but it's a stochastic relationship because it's not exact. So the data that you're going to get comes from a deterministic relationship, which is learnable in principle, f star, and some random noise. And here actually we use conditional probabilities, which is good that we talked about it. Random noise, which is centered, independent of x, and often normally distributed. It's not always independent of x. This is maybe a strong assumption, but let's make it for now. So what does it mean? It means that for, say, the age of the person is X, is 30 years old, then what's the probability that you will observe a certain height, right? It will not be deterministic, but it will be stochastic. So, and one way to model it is by using noise, by saying, okay, there is some underlying function which tells us how the relationship is, but there is some noise, maybe because the truth is just noisy, or maybe because our measurement devices are have some noise, are not exact. And so instead of observing this exact y value, well, this is kind of a 3D plot in 2D, we observe kind of some other value, one of these dots here, which stem from this probability density. So somehow these points close to the true function value are more likely to be observed than the others. If we make many realizations of this, first of all, the joint density will then look like this, right? So there is some, as we call it, prior on X, some distribution of X, and then if we multiply it by the conditionals, which looks like this, then we'll get this joint density plotted here as a contour plot. I think you're all familiar with this by now. The reason why we don't see anything here and here is that in my example, the data X is just not completely random, equally random, or uniformly random over the whole interval. The X values here in the middle are just more likely than on the outer ones. This is why you get this contour plot in this specific example, which I chose manually. Okay, so what will the data look like? The data will be a set of random realizations from that pair. And we will always assume that they are IID. IID means they are independent and identically distributed realizations of these random quantities. Sorry. So basically you take several random points from that distribution, right? But they have to be independent. They cannot all lie on that line, for example. Okay, so they have to be really, so you take random people from the population, if you like. You don't take, oh, okay, I'll just take male people because I'm uncomfortable talking to females or whatever, or I'll just take children because they're easier approachable. Sorry for being creepy here. But I hope you know what I mean. So they have to be really random in the sense that they are independent. And then you have this data set, and remember, you want to learn the function. You don't know the function, you don't know the density, you only know the observed data, right? So think of it of only having the red points and trying to recover the blue function approximately, okay? Okay, how do people go about this? So the strategy is as follows. You first subdivide the data into different sets: training set, test set, and validation set, which we'll go into in a second. Then you define a loss function. You choose a hypothesis space, which basically tells you which functions are allowed. And this will be very important to choose it meaningfully. We will talk about this a lot. And then you optimize, meaning that you try to fit the data using functions from that hypothesis space by optimizing the loss function you defined, by minimizing that loss function. We will come to all of that in a second. So let's begin slowly. So subdivide the data. The data is typically subdivided into training data, validation data, and test data. The training data you use to actually train the model. So this is what you actually use for fitting. You forget some of the red points basically and try to fit the other ones. The ones you forgot, this is kind of, surely that's a waste, but you will need them later, as you'll see in a second. Okay, so this is the training set, the biggest one, 60 to 80% typically, you use for the training to fit, to do the model fitting. And then the second part is the validation set. The validation set is used for model selection. So how to choose the space of functions by which you try to approximate your true function, right? So the parameters, how do you parameterize your model, right? for example, if you're using polynomial interpolation or polynomial regression, how do you choose the degree? How you choose the architecture of a feed-forward neural network if you want to approximate f by an fnn? It's used for tuning hyperparameters and detecting and avoiding overfitting, underfitting. This is something that we will come to later, which will also be very important. And it's used during training, but not directly for training itself, not for the fitting process, right? So you basically try to choose the model, choose the parameterized model using the validation set, and you use the training set to then fit the exact parameters, the values of the parameters. Okay, and then in the end, you use the test set to actually assess how well your estimated f, right? After training, you have an estimate of the f, how well it performs. It's there to estimate the expected loss. It must never be used during model selection or fitting, otherwise it will be later you will get a bad estimate because you lack independence and you will get a bad estimate of your performance. And then when you start getting new data, you will realize, oh boy, my performance is much worse than I expected it to be, right? So leave the test set out of the training and only use it afterwards. Then you'll get a good estimate of your generalization because then it will show you how it really performs on new, completely unseen data. Okay, so this is step A. Step B is defining the loss function. This consists of two steps. First, you define the pointwise loss, the loss of at a single point, basically. For example, quadratic loss. You will see this in a second why this is meaningful. And then you define the training error, the so-called empirical loss, by doing the following. You compare, so you have some f, some candidate for, this is not your best fit. This is just some fit. Just some candidate for your function, and you compare how good it performs by comparing f of xn with yn. So you typically look at this distance between f of xn and yn. Okay? This distance, for example, you can square it or apply a different function to it. For this workshop, it's totally fine if you just think of the squared loss, the quadratic loss. So you take the distance, you square them, and you add them all up. If the resulting sum, actually take the mean, so you divide by this one, but this is not important. If the resulting sum is small, then it is a good fit. If the resulting sum is very high, then you have a bad fit. So this is the guy that you want to minimize, right? You want to minimize the sum of these distances, or squared distances, over the whole training set. I hope this makes sense. I think this is really important to understand. Okay, then you define the validation error, which is the same thing just for the validation set, and the test error, which is the same just for the test set. This guy then really, since the test set was not used for training, this guy will approximate your expected loss. Expected loss somehow connected to generalization error, as we will see in a second. The expected loss is the expected value. I will not define it because it will be defined on Friday, I hope. The expected loss, which by the way is an integral. So integrals are important, as you see. It's an integral over the loss function times the probability density dx dy. Okay, so this is the expected loss. This is what does it mean? It's the expected squared distance of any new point coming in. So if you then take a new sample and apply f to it, right, your candidate f, and you compare it to the actual partner y of that x, then this is what you expect to get on average. The mean. It's the mean. It's the average over all possible losses, but weighted with how probable each one is, how likely each one is. That's the expected loss. That's the guy that you actually would like to minimize, but you cannot actually minimize it because you don't know the density, right? You only have training data, so you actually minimize the training error instead, the empirical loss. That's what you can do. This is something you cannot do because you don't have access to the joint density. You only have the data. Okay. This you can do for every f, right? For f star, for the true one, it's likely that it's pretty small, the error. But for others, it can be big or large, and you want to choose the one for which it is small. But we have to be cautious here not to overfit, as you will see in a second. Okay, the third step that we are going to talk a lot about is the hypothesis space, H, that you choose your estimate of f from. It has to be adapted to the problem at hand. So sometimes you know from physics how to parameterize your model because you know the parameters have physical meaning. You know how they enter into the physical process. But they also have to be adapted to the available amount of data. So if you have a lot of data, you can use a complex model. But if you have very little data or very bad data, very noisy data, you shouldn't have too many parameters in your model. This is considering the so-called bias variance trade-off and to avoid overfitting and underfitting. That's the issue here. That's what we're going to talk about in a second. And this you can control by using the validation set to some extent. Okay, and that's what I wrote here. You can adjust the hypothesis space, so the parameterized model, how you parameterize it, not setting the parameters. Setting the parameters is really the fitting process. But setting up the model, how the parameters enter into F, this is choosing the hypothesis space, and this is what you do using the validation set. Okay, and the final step is then, of course, the optimization itself. You minimize your training error, your loss, your training loss, your empirical loss, over all possible functions from the hypothesis space. This is how it all enters. The data enters in the loss function because it enters in the training, in the empirical loss. The loss function enters because that's the guy you want to minimize. The hypothesis space enters because that's the space that you minimize over. So only candidates from the hypothesis space, only certain functions are allowed. And this guy I call f-stat. This is the one that you want to minimize. In practice, you won't get f-stat exactly, right? The statistical estimate. Instead, you will get some approximation to it just because the optimization problem is too complicated, typically. So you won't get the true minimizer, just hopefully an approximate minimizer, hopefully a good approximation to it. And this will be your f-hat. I should mention the Bayes estimator. The Bayes estimator is a theoretical guy. This is not a practical guy, something that you cannot do in practice. It's the minimizer of the expected loss, the true loss that you would get if you had the whole knowledge of the whole density, which you don't have because you only have the data. This Bayes estimator, as I said, requires knowledge of all of the whole density of the whole distribution of x and y. More precisely, the conditionals of y given x are enough, but we are not going to talk about this. And this corresponds to an infinite amount of data. So you need infinitely many samples. And we should stress that the Bayes estimator is not always f star. It depends actually on the pointwise loss, right? The L here was the average over the pointwise loss. And depending on how we choose the pointwise loss, we get a different estimator. So f Bayes will not always be f star, but it will be f star for the standard quadratic loss. Okay, so this is provable. Yeah, why should you even choose other losses? Because sometimes you want to be you don't want to minimize the distance, but you want to be maybe somehow risk averse in finance, you want to be sure not to lose it all, basically, right? Even if losing it all, it has a small probability, you maybe want to avoid it completely, and so you can adapt the loss to it. So really penalize situations where you kind of lose all your money or something like this. So you want to be risk averse in that sense, and there are risk averse losses, and there are also some information theoretic losses which are also interesting, but they are also out of scope. Okay. So the Bayes estimator is kind of the best possible estimator that you can get, but it's only a theoretical guy because you cannot get it in practice. And as I said, you optimize, and if you see, oh, I'm overfitting, then you should validate. You use the validation set to validate H and possibly retrain your model afterwards, right? So you say, oh, okay, my fitting, I was completely overfitting. The performance on the validation set is horrible. I will adapt my model. I will choose a different parametric model, and then I will optimize again on those parameters. Okay, so C and D kind of go hand in hand, right? This is why training and validation sets also go kind of hand in hand. You choose a parametric model, you optimize, you check on your validation set, oh, we are overfitting or we are underfitting. Let's try again. Let's adapt the model, train again. So it's an iterative process, which can be very costly, but this is how it works in principle. Okay, let's talk about the different errors that we are making. So the best estimator, the theoretical guy, is the base estimator. It's the best possible F to fit an infinite amount of data, right? We cannot get this because this guy might even live outside our hypothesis space. The guy in our hypothesis space, which minimizes the expected loss, let's call it FH. This is a different guy, and the error that we make here is called the approximation error, right? The error from choosing an approximation space that is smaller than the whole space of functions. That's the approximation error. This guy is also a theoretical guy. We cannot get it, right? Because still here we have the expected loss and not our training error, not our empirical loss. We don't have L of F. We cannot evaluate L of F, and we cannot optimize that over the hypothesis space. So this is also a theoretical guy. Instead, we optimize not L of F, but L train of F to get F stat. Yeah, so this is called the estimation error or statistical error, which comes from the fact that we don't have enough data. We don't have an infinite amount of data. We have a finite amount of data that we train on. And from that statistical perspective, we get another error, which is called the estimation error, because we optimized the wrong L. And finally, we even cannot find this F stat, right? That's, as I said before, F stat is in some sense also a theoretical guy because it's the true minimizer. We cannot get always to the true minimizer. It's hard to find. So we will see that when we talk about gradient descent, that the true minimizer is hard to find. Instead, we'll find some other guy, which will be our actual estimator, because the optimization process is too complicated to perform. Solving this problem is too complicated, and this optimization then gives us the optimization error. Okay. So in formulas, if we compare the expected loss of F minus the smallest possible expected loss, this is called the generalization error or the excess risk. Some authors call this guy the generalization error, but this formula is more common. So this is something how you would estimate what you would like to use to estimate the performance of your algorithm, of your model. Then, as we do in mathematics, we plug in zeros. So we do the following trick. We take L of F hat minus something plus something minus something plus something, which gives basically 0. So this is allowed. And what is left is minus L of F base, which is this guy here. So we basically plug in these 2 points in between, and we get these 3 errors. So this whole error is decomposed into these 3 errors, which are the optimization error, because we cannot find the exact minimum, right? Our optimization problem is too complicated. The estimation error, the statistical error, because we have only a finite amount of data. It vanishes as the data goes to infinity. And the approximation error, which depends on the model class H, and which tells us how close our approximation space basically is to the true, to F base. And oftentimes, as I said, if you have the quadratic loss, then F base is actually equal to F star, and you want to find F star, right? But if you want to be more risk averse, you don't even want to find F star, you want to find F base. But that's how it is. Then you define the loss appropriately. Okay, let's move on. Now, the point that I really want to stress is the bias variance trade-off, or the overfitting underfitting aspect. Let's consider the mean squared error. I am not sure that we will talk about this on Friday. I hope you will. And the mean squared error is the expected quadratic error, but we look at it only for a fixed x and a fixed y, which is f star plus epsilon. The epsilon is random though, right? And the data set, recall the data set xn, yn, is random as well. So if we look at the average here, it's first of all the average because we have some noise, but it's also the average over all possible training data sets, if you like. So the mean squared error of our f hat is defined as this expected value, which I hope you will talk about on Friday. And it can be decomposed. So there is a lengthy calculation, which I'm not going to show because it's boring. A lengthy calculation which gives you this decomposition. And the decomposition is very interesting. Let's look at it. So it contains a term we call bias squared, so the squared bias term. What is it? Consider the mean over all possible f hats. So since you have the mean, as I said, you take the mean over all possible data sets, right? So depending on your data set, you will get a different f hat, and you take the average f hat. How does the average estimator differ from f star, from our true function? This is called the bias. So it's basically like the systematic error. Even if we had many different data sets and we would average over all of our f hats, we would still get some shift, and this is the systematic error of our procedure, which we call the bias. And if we square it, it's the squared bias. Then comes the variance. This tells us how wide our estimators are spread from the expected estimator. Again, this is the expected estimator, the average over all possible estimators, right? And we look at how different f hats differ from that mean. Okay, so how strongly are they spread? Are they all close to the mean, and that's why the mean is there? Or are they widely spread, and the mean is still sitting somewhere here? Okay, this is the variance. We take the distance, we square it, and we take the average. The average distance, that's why how widely spread they are, the average squared distance. And then what remains is the noise term, and this is something that you cannot learn. Okay, so basically you want to minimize the mean squared error, right? You want to minimize the mean squared error, but the noise guy you simply cannot minimize. Okay? That's because it's random, it's stochastic. You cannot learn it, you cannot minimize it, and you shouldn't learn it. No algorithm can do it. That's intrinsic in the problem. Okay, so how does it look like? So this orange curve, you can think of the expected loss, but you can also think of the mean squared error if you like. If you average this guy over all possible x's, you get L of f for the quadratic loss at least. Okay, so what happens? On the x-axis, we have the model complexity. The more you increase your complexity, so the bigger h becomes, the space of functions that you consider, the better you can fit the data, because you have many more functions, so you can really get close to the data because there are more functions to choose from. So your training error will decrease. But at some point, somewhere around here, you will overfit the data, meaning that you are fitting noise from the data instead of fitting the function itself. I will show you this in a second in a very good plot. Okay, so stick with me here. Overfitting means you are too close to the data. Your model is too complex and you have too little data to allow for this complexity. And at this point, you start overfitting. Your training error goes down, yeah. But if you then look at the test error or at the expected loss, you will see that it will go up. Even the validation error, it will go up. And this is bad, right? You are overfitting. The model is good on the training data, but it generalizes really poorly on new or unseen data, even on the validation set and the test set. Okay. In this area, your model is not complex enough. You are underfitting. And in this area, you are overfitting. Here you have a low variance, typically of your estimators, and a high bias, because you simply cannot fit the function. Your model is too simple. It just doesn't fit the true function. The true function is too far away. While here you have a low bias. You can, in principle, fit the function, and the expected guy will be small, but your variance will be very large. Depending on which data set you use, remember the data set is random, you will get a very different result. So you get a whole spread of different estimators f hat. If you use different data sets, they will be not similar at all. And this is bad, right? Because it guarantees you poor generalization, right? You will not be able to generalize to new data. So there is a sweet spot which tells you how to choose your complexity, your model complexity. And this sweet spot, you basically use your validation set for, right? To not overfit. I should add that if you have more data, or you have better data in the sense that the noise is smaller, then you can allow for higher complexity, because then this curve would shift to the right and your sweet spot would shift to the right as well, and you can allow a more complex model with more parameters. But if you have little data, use a simpler model, typically. Okay. Now, let's summarize again. Underfitting means your model is not complex enough. If your model is not complex enough, you will get a high bias, a very high bias. You will get a low variance, but the training error and the test error both will be high. So you will have a poor performance and poor generalization. In overfitting, your model complexity is too high. You have a model that is too complex, too many parameters, roughly speaking. Then your bias will be low because you can basically fit many functions, but your variance will be high. Because depending on the data set that you get, you will get a very different result. The training error will be low, but the test error will be very high. So you cannot really use this model in practice for new data. And if your model complexity is appropriate, so you have a good balance, like with the sweet spot that I was talking about earlier, you have a moderate bias and a moderate variance, and the two errors are sufficiently low, and then you can go with it and perform well on new unseen data. Okay, now as promised, some visualizations. I actually have two visualizations, I think. Okay, so one you have already seen here, and these are two new ones, left and right. On the left, you see a fit with a polynomial of degree 15. We have 20 data points, and we use a polynomial of degree 15 to fit the data. You see, the training error is almost zero. We basically, by a polynomial of degree 15, we can basically hit all the points almost exactly. So the training error is very small. But as you can imagine, this function is very far from the true function and will generalize very poorly on unseen data, right? So if I use this guy and I use a different data set, the function will look very different. Different data set, different data set, different data set, different data set. And here is a schematic plot showing that, yeah, your average value is somehow close to f star. You wiggle around this f star, but you are almost always far away from f star. So you have a very high variance. Depending on your data set, you get a very different result. This is overfitting. If you're choosing a degree that is too low, say degree 1, so using a linear fit or an affine fit, more precisely, then you have a strong bias. You cannot possibly fit the data well because the model is too simple. So depending on the data, you will get different results. They kind of are much closer than they were before, right? they kind of are rather similar. So you have a small spread, small variance of the f hats. They are basically all very close by one another, but they are far away from f star, which you want to learn. So you have a strong bias. So this is underfitting. And now, if you use a meaningful, a good balance, an appropriate model complexity, for example, a quadratic fit, then you will have a small loss. You will fit the data well. You will have a small training error. They all look very close to one another, no matter what the data looks like. So you have a small bias and a small variance, and this is what you want, right? I mean, in the end, you will only see one f hat. You won't see many f hats because you have just one training set. So this is a theoretical analysis that we're doing, right? We don't have 20 different data sets. We have one data set, and depending on the data set, but theoretically, depending on the data set, you get different results, and you want them not to be too different, right? Because otherwise your generalization would be bad. I hope you get my meaning. It's hard to do this in an online course because I don't see your faces nodding as I explain this, but I hope this explains what I want to say. Good. This is a slide that I don't want to go into because there is too much text, but I just wanted to show you that there are different parametric models, and the most common ones are linear regression, where you have an affine function in higher dimensions. You have polynomial regression, that's what you have just seen, polynomials of degree 1, 2, and 15, which also can generalize to higher dimensions. We also talked about neural networks. This is a way to parameterize a model. Those are certain parametric models. And then there are also Gaussian processes, which are somehow more abstract, I would say. They're not parametric, they're non-parametric models, but they have a very nice interpretation, and I really like modeling things with Gaussian processes. They're really beautiful. Again, I will not go into the slide too deeply, but you can look at it afterwards if you like. In practice, sometimes you want to choose a very specific model because, I don't know, for some reason, maybe you have some physical intuition for your model, or your data seems to have some patterns. You decide to choose a very specific model. Here, this is just as an illustration purposes. This is a very uncommon model. So we have our model has two parameters, theta 1 and theta 2, which are combined into a vector theta in R2. And it looks like this. It takes theta 1 times x, adds 1, squares it, and it adds such an oscillatory term, and the frequency of this oscillation is theta 2. That means that your hypothesis space are all such functions. All such functions with different theta. Let's have a look at it. Okay, in fact, what I didn't tell you, the true function f star, that's how I chose the example. I produced it from such a theta, namely for this specific theta star being -1, 1.4, -1, 1.4. For this theta star, the function looks like this. And as I just said, this is exactly our f star, which I used to generate the data. For different thetas, we will get different functions. Let's have a look. For this theta, say 0.2, 1.48, the function f theta looks like this. And you see it doesn't fit the data very well. There is a huge loss. There are huge losses here and there. Pretty good here, but very badly here. And the overall loss is this guy here. I dropped the index here because from now on, we are only going to talk about the training error. I'm sorry for this. So this is the empirical loss, and we will not divide the data. So think of the data as being already the training data, and this loss will always be the training loss from the empirical loss, the training error, from this point onwards. Okay, so the subdividing the data part is over. We concentrate on the training data, and this is our loss that we want to optimize. Okay, so you see, for this theta, we get a different function, and for this theta, we get again, a very different function. This one fits slightly better. The empirical loss is 190. Here it's very bad. For this theta here, 1.57, 2.14, we get this function. So I just want to give you an intuition. For different thetas in the theta space, we get different functions. and the different functions have different losses. And we want to choose the theta with the minimal loss. Okay. Okay. So most of them have a very high loss, but some surprisingly have a rather small loss. For example, this one fits also pretty well, even though it's somehow far away from the true theta. And this one also fits pretty well. This is almost a quadratic fit, where you don't have this sine term at all because it's set to 0, theta 2. This also fits the data pretty well, so it's somehow close to the performance of theta star, even though it's far away from theta star. And altogether, that means that for every theta, we get a function, and for every theta, we can compute a loss. The loss is a function of theta. Okay, so this is the important part. The loss now becomes, if we parameterize, actually the loss is a function of f, but through the parameterization, it becomes a function of theta. I hope this illustration has made things clear. And since it's a function of theta, we can now plot it over theta, right? As I've shown you, for different thetas, we get different values, and now we can plot those values, right? For every pair of theta 1, theta 2, we compute the loss, as we did before, and plot it. So we get this loss surface, which, by some weird coincidence, is exactly the surface that I have showed you before when we talked about function visualization. Okay, so this is the loss. Here is the contour plot of the loss. And you see certain pairs of theta perform pretty well, right? That was our quadratic fit. That was this other fit, which performed not too badly. The theta star performs pretty good, but actually there is a theta, which we call theta stat, which performs even better. How come? Well, there is some noise involved, right? No one tells us, hold on a second, no one tells us that the true f star is actually the best one in fitting the data, right? Because there is noise, so some other function might actually fit the data better than f star. And that's the case here. It happens to be very close to f star, and you see that's the true minimum of our loss surface. Okay. How are we on time? Oh, we're right on time. That's good. Then let's talk about optimization. I hope, okay, let me make a break here. So what we have talked about is that the hypothesis space has to be chosen with care. You have to consider the bias variance trade-off. You have to consider underfitting and overfitting, which is related to it. Once you have chosen your hypothesis space and it's fixed, it's typically a parametric model, and you try to minimize the loss, which is now the training loss. I just write L. You try to minimize that loss over theta. This is the next step, and this is the optimization step. We won't typically find the best optimum, the best minimum, but we want at least to get close to it. Okay? So we won't really find this point, this red point in general, but we want to get close to it. Let's go. So optimization, how do we actually minimize such a function? Okay, and the idea is gradient descent. Remember from our first part on calculus, the gradient shows in the direction of steepest ascent, so the fastest increase of the function. Meaning that the minus the gradient shows downhill. Right? It shows exactly in the direction of steepest descent. So this motivates the following algorithm. You start somewhere for some theta. You consider your loss and the gradient of the loss, and you make a small step in the negative direction of the gradient. So a small step downhill. The eta is the step size, also called learning rate, and we will talk about this a little bit. And we will talk about how this gradient can be computed. And then you hopefully go down your hill to the valley and end up in a minimum, right? This is the way, going down the valley, down the slope of your hill and finding the valley. How do we compute this gradient? Well, if L of theta is a quadratic loss, then we can simply apply the chain rule, okay? So the outer function, okay, the outer function is the sum. The sum stays the sum. We don't care. The inner function is the square. So no, sorry. So the outer function in the sum is the quadratic. So we have to take the derivative of this quadratic, which is 2 times the inner guy. This is the outer derivative, evaluated at the right point, theta, times the inner derivative. The inner derivative is the gradient of this inner guy, which is just the gradient of f, but with respect to theta, right? The xn's are fixed. The xn's are our data points. They are fixed. The theta is the guy that we consider L to be a function of, and the theta is the one that we want to optimize in. Okay, so how do we compute the gradient of theta? The gradient of f with respect to theta. Let's have a look. If f theta of x is our function here, then the gradient, well, we have to take the derivative with respect to theta 1. This guy does not depend on theta 1, it's a constant, so we can ignore it. We have to take the derivative of this guy with respect to theta 1, and we get, again, by the product rule, by the chain rule, 2 times theta 1 x plus 1 times x. Please be careful here to take the derivative with respect to theta, not with respect to x. Theta is your variable here. And this the derivative with respect to theta 2. For this, we only have to consider this part because that one is constant in theta 2. And the derivative of this part with respect to theta 2 is just 8 times the cosine times the inner derivative with respect to theta 2, right? Which is x. So this is how you build the gradient. For a feed-forward neural network, we also know how to build the gradient. You use, again, the chain rule again and again and again, using the backpropagation discussion that we had before, right? So by backpropagation. In general, it's hard to find the gradient, but for these 2 examples, we can actually compute it. Okay, let's do an example. Sorry for the long talk on how to compute it. Again, we start somewhere, and we want to minimize our loss. We look at the gradient of L. The gradient is always perpendicular to the level curves, right? Because it points in the direction uphill. It points uphill, but we go in a slight step in direction of minus the gradient downhill. We go a small step, we look again, and take the gradient of that point, right? Oh, okay, the gradient points in this direction, so we take minus in that direction. Now the gradient will point perpendicular to this line, and we make a step in that direction. Then the gradient looks perpendicular to this line, and we make a step in that direction. And this is how we find the minimum, right? Unfortunately, there are local minima here and here and here, and we might end up there. So if we start with a different point, right, our initial point was random, we could also end up in some other local minimum, which is bad. Right, so the gradient descent can get stuck in local minima. This is a problem. Okay, let's talk shortly about the step size. The step size, if you choose it too small, you will have to make many steps. And taking these steps is costly, right? You have to compute the gradient. This is costly. So you will take very long to converge to the minimum. If you choose eta too large, then you have a risk of overshooting and divergence. So say you are somewhere in the Alps and you want to go down the valley and you look at the direction that you need to go, but instead of going for 10 meters and looking again, you go for 100 kilometers in that exact direction. Then you will end up on a very different hill, somewhere completely different, and look again, telling you to go somewhere else. And then after 30 iterations, you might end up somewhere in China, right? And not where you wanted to go. So eta must not be chosen too large, and there are some strategies to tune it. But we are not going to talk about this today. This is out of scope of this workshop. What I want to talk about are the limitations of gradient descent. One, we have already seen, the gradient descent can get stuck in local minima. Of course, you can start in different points and use several gradient descents, but oftentimes your loss surface looks really rough. It looks more like this than what I've showed you. And imagine here finding the true global minimum. if there are so many local minima involved. All over the place there are local minima. And this is actually the case how it typically looks like, especially in high dimensions. In high dimensions, I mean, it's hard to draw and to imagine, but in high dimensions there can be many, many local minima, for example, for a neural network. And the other problem is that the gradient is very costly to compute. So imagine you have a huge parameter space. Say you have a feed-forward neural network. It has thousands of parameters. So your dimensionality of theta is, say, 10,000. You have 10,000 parameters in your model. And you have an enormous amount of training data, say images. You have millions of images. So you have to sum, and you have to sum to compute the gradient. You have to take the sum over all the images, 1 million summons, 1 million terms, and for each term you have a vector which you have to compute of 10,000 entries, right? So then you get, in the end, you get again a vector of 10,000 entries, but you need to compute a million gradients of f with respect to theta. This is really, really costly. I really want to stress this because this is typically infeasible. So you have these two problems. For small parametric models, it's fine. If you don't have too much data, it's fine. You can do gradient descent. But for bigger problems, where you have a lot of data and many parameters, it becomes unfeasible. And also you get stuck on local minima. Which brings us to stochastic gradient descent. Stochastic gradient descent doesn't optimize over all the data. It works very similarly to gradient descent. It starts somewhere, and you choose some learning rate. But instead of minimizing your true loss function, L, you only consider L on a mini batch. You take a subset of your training data, a smaller set, say your training data can be millions of images. You take just 10 of these images, and you consider the loss for these 10 images instead of the million ones. This is not the true loss, right? It's the wrong loss. But it's much easier to compute, and the gradient is also much easier to compute. And then you update using that loss, and then in the next iteration, you choose a different mini batch. Therefore, there are different strategies to choose the mini batches. You can choose them randomly, as I typically do. You say, okay, I want a mini batch of size 10. So I choose randomly 10 data points, 10 images, for example, 10 data points, and I use that as my mini batch. Or you can kind of split the data into fixed mini batches and go through them one by one, cycle through them sequentially. When you go through all of them exactly once, this is called an epoch, and then you can go through them again and again. Or after every epoch, you can shuffle and resample the mini batches. So you choose new splittings of the data for the next epoch, right? So there are different ways to choose the mini batch. The simplest one is just randomly. You just choose 10 random, for example, 10, doesn't have to be 10 random data points. How does it look like? On the left, you have our true loss function, which you already know, and our true full data, and the true f star, which we don't know, which we actually want to find, and the true theta stat. Now, here we have chosen a mini batch. From these 20 data points, we have chosen 5. We consider the loss for these 5 data points, right? Remember the black lines going from here to the function, not to the true function, but to the function corresponding to the current theta. This gives us a loss, right? So the loss depends on the data. And now, since the loss considers only these 5 data points, we average our pointwise loss over all these 5 data points. We get a different landscape. Do you see this is a different loss landscape to this one? It's kind of similar. It looks close to it, but it's different. So you start somewhere, say here, and you make a step in the direction of minus the gradient of that new batched loss function, right? You make one step, and then you would look again. But when you look again, you choose a new batch, a new mini batch, right? So instead of going now in that direction, perpendicular to this level, this contour line, you consider new points, redefine your loss. So we have chosen new 5 points, completely new loss, and make a step in that direction. Okay? Then you look at this theta, you choose new points, a new mini batch. Again, the loss landscape changes, and you move around. For some mini batches, the loss looks very different, and you can actually move around kind of randomly, but not completely randomly, because you're still somehow fitting the data, just the mini batches of the data points, right? You are fitting it in each step, and this is how you move around. And you typically, because these minima, they have a meaning, right? These local minima, they kind of fit many data points well. This is why you tend to linger around these local minima for some time before escaping them. And you then come to this best kind of local minimum here, and then you linger around this one. And this one is really hard to escape, because that theta star really fits many, this red theta stat really fits many data points well. So no matter how you choose the mini batch, for almost all of them, this theta stat will be pretty good. So you will linger around this minimum longer than around this minima. So you will tend to stick to the true minimum. Okay, this is how it looks like. So you walk around choosing different mini batches and have this trajectory here. Yeah, so you introduce some noise, and it has, again, two main advantages. The first advantage is you can compute it. Instead of having the sum over 1,000,000 images, you have the sum over 10 images. So it's feasible to compute. It's much, 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 much cheaper. And surprisingly, this seems like a disadvantage, but the advantage is, again, you introduce some noise so you can escape local minima, which was not possible with gradient descent. With gradient descent, we would have been stuck here, and we would have never even seen the other minima, unless we let many, many gradient descents run with different initializations. Okay. Let's make a short summary for gradient descent as stochastic gradient descent. So the gradient uses the full gradient over the whole data set, while SGD uses mini batches. It's therefore much cheaper to compute and much easier scalable to more data, because you can, even if you have 10 millions, 100 millions of images, you can still just use a mini batch of 10, right? So it's scalable. While here, the gradient descent is very slow. It needs to compute a very complicated gradient. The trajectory of the gradient descent is smooth and deterministic. There is no noise, no stochasticity involved, while the stochastic gradient descent moves around quite stochastically, because you choose a different loss function in each step. The gradient descent converges to a precise local minimum, but it is a local minimum, not a global one, while the stochastic gradient descent tends to oscillate, to wiggle around the local minima, and the deeper the well is, the longer you wiggle around, because it's harder to get out of it, roughly speaking. The gradient descent can get stuck in local minima, which is a huge problem, while SGD in principle can escape them. There is no guarantee for this, but in principle it's possible. This is why the gradient descent is more used for small scale problems where you have not too much data, not too many parameters, where you can actually compute it, and where maybe the loss landscape doesn't look too complicated, and you don't have, by starting several runs of gradient descent, you might find a good global minimum. While stochastic gradient descent is more feasible for deep learning, like feed-forward neural networks or other neural networks, for big, large-scale models with a lot of data. Okay, just a short remark. We talked about how to take the analytic gradient. In principle, it's often too costly to compute, or even impossible to compute, because you don't have the analytic formula for it. So what people do is auto-differentiation, which I will not go into, but you can Google it if you like. It's basically checks what the computer actually does and takes the derivative of what the computer does at that specific point without computing the formula for the derivative. Or you can use gradient-free optimization. So not gradient descent, not stochastic gradient descent, but other kinds of optimization strategies exist, which are gradient-free. Okay. Very good. We are almost done. So we are having a quiz on the data science part now, and then we'll do a wrap up after that, and then I'll take questions if there are any. Okay, so let's do the quiz. I'm not sure. Should I try to do it again online? Yeah, let me try. Maybe this will work better this time. Okay, so I started
Yes, I'm sharing the Menti
the
link.
Mentimeter, yeah.
Um,
So let's give it another try. If it doesn't work, we can still do it offline, but here I will see which answers you actually type in, so it will be some good feedback for me how well the topics were covered.
yes,
Is there a way to see if people enter or not?
in the meantime, while we wait, there's a questions in the chat.
That's a good point. Let's check the questions.
Yes,
F&A.
questions about
Explain how applied calculus is applied. So you mean by Daria Boldanova, right?
yes.
Yes. Okay, I'd appreciate if you could explain how applied calculus for data science is applied in public policy and how essential this skill is for professionals in the field. Well, public policy is such a big field. So let's make an example. For example, if you have an epidemic like we had a few years ago, then you need to make decisions, and the decisions better be based on data. And I know politicians typically base their decisions on other aspects, but it's better to base them on data and facts. And you have to make predictions, right? And for this, you need to do data analysis and regression and exactly the kinds of topics that we have covered today, right? So I hope this is one example of how such things can be used. But in general, I mean, you need predictions everywhere, weather predictions of stock markets, how the economy is going to evolve. And on these predictions, you should base your decisions, right? And something that we did not talk about is control, optimal control. Some systems you can also control, and then depending on how things evolve, and which data you gather, you can optimize your control. So I think it's so yeah, calculus and data science is crucial to make decisions for public policy. Is it possible to summarize the many data points on which SGD is calculated? So if yes, wouldn't the stepwise noise add up, making it very noisy? To summarize the many data points. Yeah, well, that depends. I mean, you can get too noisy and kind of wiggle around too much, which then indicates that your mini batch was chosen too small. The larger you choose your mini batch, the closer your loss function will be to the true loss function of the full batch, right? And balancing this is an art for itself. I'm not an expert on this, but there are strategies to choose a meaningful mini batch, and you can also adapt it as you go to choose the size of the mini batch. And this is how you can avoid getting too noisy. Of course, it becomes then more costly, right? The larger you choose the batch, the more costly it becomes. But choosing a batch of 100, say, is still much better than 10 million, right? And also, I should say that the first stochastic gradient descent algorithm used mini batches of size 1. So it used just one data point per iteration, and it still was used. Okay, so this is kind of maybe even the standard SGD algorithm using just mini batches of size 1. Okay. can I start the Mentimeter?
I think it still has some issues, so maybe we can do it directly on this.
Okay, let's do it offline again. So let me go back to my slides. I hope you all see my slides, right? So what you should see now is what is the role of the expected loss in regression?
Yes, we see it.
Yes, okay, perfect. So A, it stores data. B, it contains gradient information. C, it quantifies the prediction error. Or D, it adjusts model complexity. Okay, I'll make all these short breaks for you to think. And also I should say, in this quiz, there are several answers possible. So some questions have several correct answers. Okay, so the answer here is it quantifies the prediction error, right? The expected loss is exactly the average over the error that you're going to give from a new random data point. Very good. In the bias variance decomposition of the mean squared error, which component cannot be reduced by modeling? Is it the bias, the variance, the noise, or the training error? Okay, so the noise is the guy that you cannot reduce, possibly, because the noise is intrinsic in the data. It's something that is not learnable. You cannot learn the noise in a meaningful way. And you don't want to learn it. You want to learn the underlying function. So this one, you just cannot get better than what the noise tells you. What does a high variance in a model typically indicate? The model fits the training data poorly. The model generalizes well. Predictions vary significantly across training sets. The model overfits the training data. So the answers are C and D. So the training data will actually be fit very, very well. Too well, indeed. So this A is wrong. B is also wrong because the performance on new data will, again, be very, very poor, right? So it generalizes very poorly. And the reason is that the prediction depend enormously on how the training data set looks like. So if you take a new training data set, choose it randomly, you'll get a very different result. So C is correct. And the problem is that the model is strongly overfitting. Now, what are the main drawbacks of selecting a model with very high complexity? Is it high bias, high variance? Are you overfitting the training data, or won't the model converge? Okay, if your model is too complex, you will have a small bias, but a large variance, right? So you can in principle fit your F star well, but you won't because you are overfitting the data. So B and C are correct. Good. Next question. Which of the following can be used to avoid overfitting in statistical learning? So what can you do to avoid overfitting? Reduce the model complexity. Increase the training data size. Reduce noise in the data. So basically have better data. Or a validation. And the answer is all of them. So reducing model complexity is good because then you can avoid overfitting because your model becomes simpler and you won't, that's what we talked about basically, right? Maybe you will underfit at some point, but you won't overfit. Increasing the training data size, yeah, if you have more data, then you can allow for a more complex model. If you have better data with less noise, part C, you can also allow for a more complex model. And D, validation, this is what is typically used to adopt basically the model complexity in the end, right? Or choose a better model. You can use validation to compare models and choose a better one which will not overfit. And actually, there is a fifth answer, which we did not talk about today, but I wanted to put it here. That's regularization. There are many regularization techniques which we did not talk about at all. Basically, or the most typical one is to slightly modify the loss function to add a term which prevents the function of being too wiggly. Yeah, this is a very rough intuition for regularization. So you change the loss function, you don't optimize the true loss function, but you optimize some average over the loss function. You want to fit the data, but you don't want your function to be too weird, right? So you penalize weirdness. Okay, sixth question. If a model underfits the data, what is likely true? It has high bias, it has high variance, it uses too many parameters, or it performs well on unseen data. Well, if you find that the model underfits the data, then you are in the underfitting regime where you have hold on, where you have low variance but high bias because you cannot fit the true F star well. If you underfit, you are using a model that is not complex enough, so you have too few parameters, not too many, and it will not perform well on unseen data. What are the primary benefits of SGD over the full gradient descent? So does it guarantee convergence? Does it reduce the bias? Does it have a lower cost per update? Or can it escape local minima? And okay, the convergence is not guaranteed, and we cannot really say anything about the bias, but we definitely can say that the cost is lower per update. Sometimes we will need more updates because we wiggle around more, but the cost per update definitely is smaller. And in principle, we can escape the local minima so that we, at least theoretically, can find the global minimum. By the way, something that I didn't say when I talked about SGD, if you like, you can track your true loss function over the thetas produced by SGD. So you can, sorry for that I didn't explain it later. The quiz is over, by the way, so the wrap-up is coming, so I I'm allowed to go back to this slide here. If you like, you can evaluate the true loss in all the points that you have and kind of track the loss function as you move along SGD. Then the true loss, as you move around, might get larger and smaller and larger and smaller, right? Because you kind of, depending on where you land. And you can really see how at some point you get to the global, roughly the global minimum. You won't hit it exactly, but you will go to the roughly the global minimum and wiggle around there. And when you see, okay, we won't get better, maybe we even get worse because we escape the deepest well and go to this well, the loss function will get higher again, then you know, okay, maybe I should have stopped here and call it a day. Because there is no guarantee of convergence, but you can track the true loss function as you evolve and find kind of the minimum, at least, of the true function over the iterates, of the SGD iterates. Okay. Okay. I guess I'll first do the wrap up and the questions then, because there is a Q&A at the end of the wrap up. And the wrap up is also not too long. So the key takeaways from calculus are: functions describe certain relationships between different quantities. Their derivatives measure change, so rates, slopes, and sensitivity. I think sensitivity is a good intuition as well, which is sometimes overlooked. Integrals, on the other hand, measure accumulation, like areas or hypervolumes, and can be used for probabilities, to quantify probability distributions and so on. And somehow they are the inverse operations to derivatives, because accumulation is the inverse process to considering the rate of change. We talked about vector calculus because we needed it in RD, right? All of machine learning happens in high dimensions. So we need vector calculus. And we extended all of the ideas of derivatives and integrals to higher dimensions. And we talked about partial derivatives and gradients in particular, which have a clear geometric interpretation. Please remember that the gradient points in the direction of steepest ascent. The chain rule helps understand complex layered models. And so if you have many composed functions, one after the other, and it can be applied to feed forward neural networks in the form of backpropagation very efficiently. Okay. For data science, where we mostly focused on regression, we talked about how to learn a relationship, a function, f star, between some input x and some output y, which we assumed to be some function of x plus noise. And we learned it from independent realizations, x and y, and which were our data. We talked about how to split the data and how to define the loss functions, which basically tell us how good does this model with these specific parameters fit the data. That's what the loss function does. We talked about how to choose the hypothesis space, how the parameters have to be chosen suitably, and how to avoid over and underfitting, which is connected to the bias variance trade-off. We talked about how to validate your model in order to choose good models. So that was the hypothesis space part. And then we talked about the training, which was the optimization step, where we actually fit the data by optimizing over the parameters, by optimizing the set of parameters. We talked about gradient descent and stochastic gradient descent. Okay, and in general, not in general, but the generalization, we talked about the generalization error, and good models should perform this not just well on the training data, but also on new unseen data. So please remember, if someone tells you, hey, I can fit your data very, very well, you should say, well, are you sure your model is not too complex? Are you sure you aren't overfitting? Is the data good enough, rich enough? Does it have enough information and large enough, the data set, to allow for this complex model? This is a question that you really, really should be asking. Okay, why should we learn calculus for data science? I come back to my motivation. So very roughly, if you model the world by mathematics, you use functions and integrals and derivatives. If you train models, you optimize functions. If you explain predictions, you interpret gradients, right? This is our sensitivity analysis we talked about before. If you look at the partial derivatives, those tell you how does the input depend, how sensitively it depends on which input and on which parameter. If you build neural networks, you need to understand the chain rule, because that's essential what you do, that you chain derivatives using backpropagation. And if you model change over time, you solve differential equations. This is something, it's in gray because we didn't cover it. And I'm sorry, we couldn't cover it. It was kind of out of scope. We didn't have enough time. We talked about the predator-prey system, though. So I'm happy we at least addressed it. It's on some level. So those are differential equations. There are ordinary differential equations and partial differential equations. And then there are the stochastic versions. And they use a lot in machine learning as well, because there, for example, there are neural ODEs or PINs, physically informed neural networks, which are mathematically not well understood, but they're used nonetheless. So it's, if I were you, I would study ODEs as a next step. Okay, what did we not cover? Well, first of all, our mathematical analysis was not rigorous. We didn't have proper definitions. We didn't state theorems rigorously, and we didn't do proofs almost nowhere. To do this, we would have needed, for the calculus part, several weeks, many weeks actually. We do this over 2 semesters, or sometimes 3 semesters. So this was out of scope for our workshop. For the foundations, we didn't talk about real numbers, sequences, series, and limits. The real numbers I kind of took for granted, while sequences and limits, we only worked with them on an intuitive level. We did not define it or even talk about them at all. Differentiation, we talked about the derivative, but we didn't talk higher. We didn't discuss higher order derivatives, so second, third derivative, and so on, which is then connected to the Taylor expansion, which we did not cover. We did not cover the Hessian, or the divergence, or the curl, or the Laplacian, which are certain quantities of differentiation in higher dimensions, which pop up here and there. We didn't talk about complex calculus or complex numbers and the Fourier transform, which is used ubiquitously in data science, machine learning, and in mathematics in general. And as I said, we didn't talk about differential equations, ordinary partial differential equations and their stochastic versions where there is some noise involved. Okay. If you want further reading and resources, I can highly recommend the book series of Kevin Murphy, Probabilistic Machine Learning. It's pretty rigorous and it's very comprehensive. It covers a lot of topics. It's easily accessible and it takes the statistical viewpoint, which I really like, which is, in my opinion, is much better than every other viewpoint. So the probabilistic approach, viewing data as being random draws, that's the way to go, in my opinion, and that's what the book series does very, very well. And I also want to recommend the YouTube channel and website of 3 Blue 1 Brown by Grant Sanderson, who does really wonderful illustration, much better than the ones I could show you. Wonderful illustration videos, which really give you an intuition for these topics in calculus and other fields such as machine learning and so on. He actually has some courses even on calculus, linear algebra, probability, and I think differential equations as well. And the explanations are superb and on point. Not too long also. It's very, I like them a lot. So I can really, really recommend this. Even if you just do it during lunch or so. You can watch these videos. They're a lot of fun. Okay. With this, we are done with the workshop for its main part. Thank you very much for your attention. If there are any questions, I'm here for the next 30 minutes. We have 30 minutes for questions, which is good. Okay, so there are some questions already. How can a model not remember the training data? The actual gradients are created based on it. The form changes, but ultimately to me, it seems like that's what is remembering data. What am I missing here? Okay, I suppose you are talking about SGD. So if this is a question in general, whether the model remembers data, it totally does. Yeah, so the model remembers the data, so it's trained on the data. It fits the data. The question is, does it overfit it or not? Does it generalize well to new data or not, right? So, but definitely it does remember. It does, I mean, what does it mean remember? It remembers it in some sense. It somehow contains the information from the data. It doesn't remember the data per se. You cannot extract the data from the model, but it kind of has it in the back of its mind. If you're talking about SGD, the actual gradients are created based on it. Yeah, so the form changes over time. So the loss function changes over time. And of course, the old data does not get forgotten completely because the location where you are at depends on the previous data. So yeah, if you're talking about the mini batches, you're not completely forgetting the old batches, the old mini batches. But that's also what you want to do, I guess. I hope that answers this question. Next question by Madhu. Is there a resource, e.g. websites, online resources or literature that you would recommend? Oh, I think that was before my last slide. To see these principles in action on real-time social sciences examples alongside the graphs. Yeah, so I really recommend 3 Blue 1 Brown. He does, his team does a really good job of explaining these things and how they are applied in practice. Are there any further questions? Yes. Oh, I'm not a professor, I'm just a postdoc. Jesse, I'm quite interested in learning this course on a more detailed and extended level. What course, for example, Coursera or other online class, would you recommend? Thank you. Okay, so what I would recommend that really depends on your background and what you want to do. So if you want to learn calculus, the best way to learn calculus is to study mathematics. So go to university, and if you want to have rigorous definitions, theorems, and proofs, you won't be able to avoid learning it in our calculus courses at the university, which I highly recommend. If you are a data science person, of course, you can also study data science. I'm not too familiar with the Coursera courses. I never learned from these courses. But what I would recommend is the book by Murphy. If you have some mathematical background, not too strong, but some mathematical background to work upon, then the book by Murphy is really recommendable. Can we get this next question? Can we get the slides with the quiz with its explanations? Yes, absolutely. I will ask we to upload the slides, and I hope they will appear on the webpage, I guess, right?
Yes, once you share it with me, I'll update it on the website, and then everyone should be able to see and download it.
Okay, yeah, it's almost 30 megabyte because of all the illustrations, so I'll have to think about how I can send them to you, but we'll work it out. Okay. Any further questions? Okay, maybe I took too much time for the questions. I thought because there were so many questions at some point during the session that they would come back at me at the end. So we have 8 more minutes. I will wait 8 more minutes.
In the chat as well. So Anatole, for example, asks what programs were used to make the data visualization in this presentation?
So, since I studied mathematics, and at that point when I studied, we were still using MATLAB. By now we are using Python, but I'm so MATLAB has become so convenient for me that I did the visualizations using MATLAB. You can do all of this, of course, in Python, and in fact, I could use ChatGPT to translate it to Python. So typically, you would use Python if you were less conservative than me. And then the other question is.
I think that's it so far.
Oh, that's it so far. Okay.
Yes.
I'm a research assistant in the field of HCI. Can you decipher HCI for me? How data science is helpful to me? Can you please decipher what HCI means? Thanks. Human-computer interaction. Oh, but human-computer interaction, it works a lot with data and models, right? So I mean, I'm not an expert on this. Maybe you know better than I how human-computer interaction works. But basically, your models have to adapt to the human it interacts with. So data is coming in all the time, and the models have to be adapted kind of online to the data that's coming in to the person. So you almost all the time you are fitting models. So you have, I'm sure you have some parametric models. I don't know which parametric models they are using involved. Maybe also non-parametric models like the Gaussian process regression that I talked about. And from this, depending, of course, on what exactly you work on, you're using calculus and data science all the time. I hope this answers the question. Jayant Malik asks, I studied the concepts of centroids. If we could represent a small number of features with centroid on a graph, and then those centroids could be separated based on features they contain. And is it possible to do it without any backpropagation then? That's a good question. I'm not quite sure I understand it correctly. So the question is, of course, what your underlying model is. Backpropagation is used for feed-forward neural networks and other neural networks. I'm not quite sure what model you would use for centroids, but you would typically have to optimize some loss function, right? That's the typical approach. You do minimize something. You do minimize some function, and for this you need to take. You don't have to take derivatives. You can do gradient-free stuff, but if you take derivatives, then you'll typically have to apply the chain rule. It won't be backpropagation necessarily, but you will typically have to apply the chain rule at some point, unless you do auto-differentiation or, as I said, gradient-free optimization, which totally exists. To all those who are thanking me in the chat, thank you so much for the kind words. I'm very happy you were here, and I'm really happy that you learned something that I was helpful.
There's another question in the chat about how do math skills translate to improving ability to train ML models using Pydantic? Most of these things, which I assume are calculus problems, are already programmed. And can you give an example where your deeper understanding saved you?
Oof, this is a hard question to answer. This is a hard question to answer. So, I mean, if you have a good intuition for functions and how they work, you can just more easily grasp all these concepts from machine learning. For example, colleagues of mine or friends of mine who did not study mathematics, for them, a feed-forward neural network was like this complicated thing of bubbles and edges, and they really had to learn it. If you think about the neural network as being this complicated thing, then you need to learn every method for that complicated thing separately. But if you have the broader picture in your head that, okay, it's just a parameterized model, it's just f theta of x, and you can treat it basically as any other f theta of x, as any other parameterized model, then it's much easier to get an abstract sense of all these concepts. So for me, this is what math is all about, taking this abstract thinking, generalizing, seeing the connections between different areas and saying, okay, this is basically the same as that, right? And this is what makes mathematics unique in my opinion. And how it helps in my own experience. I mean, I work in mathematics, so it's hard to say, but all the methods that I develop are based on my intuition. So it helps a lot, and also obviously I have to prove to prove things now and then, so I do need mathematics. Okay, we have 2 minutes left. Are there any further questions? When does AGI come? I don't know what AGI is. Maybe you can answer this one.
I think it's just artificial general intelligence, which is when is the big daddies of artificial intelligence come.
Oh, sorry. Yeah, I didn't know that abbreviation. No, I have no idea. This one I cannot answer. Thanks. Okay, it was a joke. Okay. As mathematicians, we don't look into the future unless, I mean, we do predictions though all the time, but we don't do predictions based on speculations.
Yes, I think since there's no more questions, I think we can close off the sessions. So thank you very much, Asia, for very insightful workshops on applied calculus for data science. And thank you so much, everyone who joined today, and for your really meaningful questions as well. I think Asia also quite enjoy answering your questions and your jokes at the same time. I hope everyone has learned something useful for the start of this journey into mathematics for data science. And the next session will be on linear algebra for data science, which will take place tomorrow at 9 a.m. Berlin time as well. And then building AI agent at 1 o'clock in the afternoon Berlin time tomorrow as well. So I hope many of you will also be able to join us there. Thank you again, Ilja, and thank you everyone to join the workshop today, and have a wonderful day.
Thank you all for coming. I also want to say thank you, and Aliyah, for moderating, and thank you all for coming to this workshop. It was a pleasure being here. Bye-bye.